online workshop, but I'm a little bit nervous now because this is my first time to give a talk online alone. I'm just facing the screen of the MacBook and talk around. Okay, but anyway, I'd like to talk today three-level S matrix of superstring field theory. Complementary to superstring theory. The first is this is a Witten-like approach, which was originated from the work by Backwitz. And the second one is approach based on the homotopy algebra, A-infinity algebra or L-infinity algebra, studied by the Munich group, including Dick Ted. And the third approach is with an extra free field, mainly developed by Shok-sen. In this talk, we consider the heterotic string field theory based on the second approach, based on the L-infinity algebra, and show that it correctly reproduces the three-level S matrix calculated by the well-known first content method. This is in a sense that some extension or completion of the similar work given by the Sebastian Konopka for the mutual sector of the open superstring field theory. Sorry. The screen is freezed. Okay, so let me start the summary, what is the heterotic string field theory with cyclic and L-infinity structure, which is first proposed by Sugimoto and myself. And the string field in the heterotic string field theory is, has two components, the Buchwald's component and the Ramon component, which is in the so-called restricted Hilbert space. Then Buchwald sector is has small Hilbert space with Gauss number 2 and picture number -1. And Ramon part is that small Hilbert space with Gauss number 2 and the picture number -1/2 with some constraint. Yeah, these string fields have satisfied some constraints. Since the heterotic string is the cross string, that they are constrained by the cross string constraint B0 minus phi equal to 0 minus phi equal to 0. And also the Ramon component is restricted by some projection operator written by picture changing operators. We write this component on the Ramon sector is commonly used. The total phi is given to this using this calligraphic G or G inverse, which is defined by the G equal to the pi 0 plus pi 1x, pi 0, here the pi 0 and pi 1 is the projection onto the Buchwald or Ramon component. And this product G inverse is equal to just is identity on the Buchwald sector, and this projection equal to this projection operator on the Ramon sector. And the details of the forms of the picture changing operators does not need today, but just we use that they satisfy that these equations x y x equals to x and cube c equal to x. We introduced that some three kind of symplectic forms, using the symplectic form of the simple symplectic form on the small Hilbert space defined by using that BPZ inner product in the small Hilbert space. The capital omega is defined by this inserting this G inverse operator, which is a natural symplectic form in this restricted Hilbert space. And we use later also that symplectic form in the large Hilbert space, which is related to the small omega s by this relation. Okay, we also use, it is also useful that to represent these symplectic forms by using the bilinear representation, which we denote by using this Gura vector, which maps the two tensors of the restricted Hilbert to the complex number to string field phi 1, phi 2 to this form of the symplectic forms. And the heterotic string product is represented by the multilinear map from the n times symmetrized product space to the one string state. Here, this symmetrized tensor product is the space of the symmetrized tensor product defined by this tensor product with some symmetrized tensor product with some appropriate sign factor. And in particular, that L1 is just that linear map on the restricted Hilbert space we identified to the BIST operator, and the higher product is that as the interaction product representing the heterotic string interaction. And if this string products Ln satisfy these two relations, the first one is L infinity relation and the cyclic relation with respect to the simplex forms capital omega, it is called a cyclic L infinity algebra with this triple, for this triple. If we have such a string product, this cyclic L infinity algebra with proper Gauss number and the picture numbers, then the action I written by using this string product is invariant under the gauge transformation, this gauge transformation. Then assume the bosonic product, which has no picture number, is known, which is a cyclic algebra with proper Gauss number but no picture number. The heterotic string product is constructed by inserting the picture changing operator X and C0, the zero model of the Xi ghost, to this bosonic string product, keeping the cyclic infinity structure so as to have proper picture number, the picture number saturate. Yeah, it is useful that for this purpose that it is useful to use the co-algebra representation. Co-algebra representation is using the operators acting on the symmetrized tensor algebra, which is defined by the direct sum of these n strings n times symmetrized tensor product. The co-derivation acting on this the linear operator acting on this symmetrized tensor product by and derived defined by using that multilinear map Ln by this definition. Then we can consider the co-derivation formal sum of these all the string product as an operator acting on the symmetrized tensor algebra. The L infinity algebra is represented by the degree odd co-derivation L satisfying that this condition, an important odd co-derivation. Here today, I denote that this square bracket as a graded commutator. Yeah, so how to construct, we propose the construction, how to construct this heterotic string product with cyclic L infinity structure. Yeah, first consider the co-derivation with the two parameters, BST and also the lambda ST. BST is a kind of generating function of the heterotic string product with two parameters S and T, and S counting that a kind of picture number deficit, and T counting that picture number of the string product itself, and the T superscript 2R after the vertical slash is denoted cyclic Raman number. Cyclic Raman number is defined by number of Raman inputs to plus number of Raman output. Okay. Then the B is at the degree odd co-derivation, and the lambda is at the degree even co-derivation. Then construct these two kind of products, B and lambda, by cyclically inserting x0 or x0 to bosonic product so as to satisfying this differential equation with an initial condition, this initial condition. Here the T counting the picture number, then so the T equal to 0 only have that picture number 0 product. So we set if it is equal to the bosonic string product. And this condition as the initial condition, we can solve this recursively and determine all the string product with appropriate, which has appropriate picture number. Then this extended product BST satisfies these relations, which reduces to the LVT relation. We reduce the BST to the desired string product B, which is obtained by setting the S equal to 0 and equal to 1. Okay, so then if we construct such a BST, we obtain a cyclic infinite algebra in the large Hilbert space, which is cyclic with respect to the symplectic form in the large Hilbert space. We call it D minus C with this definition Q minus eta plus B. Here the B is equal to the B is equal to 0 and T equal to 1. And then starting from the B2 and just represent the interaction part of this infinity structure, infinity algebra. Yeah. And it can be decomposed. We can decompose it to two independent infinity algebra in the large Hilbert space by using by projecting to the Nebuchadnezzar sector and the Raman sector, the Q1, and we can show that this and then is the algebra which is commute. We transform them by that cohomorphism defined by using B itself by this definition to another pair of the infinity algebra by the similarity transformation this form. Then the infinity algebra C is transformed to just single operator eta, and infinity algebra D is transformed to the desired infinity algebra, which we want to construct. Then this similarity transformation preserves that infinity structure. They satisfy that this they are still an independent infinity structure. In particular, that commute with eta means that L is closed in the small Hilbert space, and the form of this coproduct co-derivation L, interaction part of the co-derivation L is that factored out at the G operator, projection operator. This means that this L operator is closed in the restricted Hilbert space. And we can also show that this L infinity capital L satisfy the cyclicity condition with respect to the capital omega symplectic form capital omega, then we can obtain that desired infinity algebra for which can be used for the heterotic string interaction. And for later use, we denote the interaction part of this L operator. It's just the L sub int, which is defined by this second term, and denoted by the small l. Okay, so next we consider tree-level how to derive the tree-levelized matrix. First, I fixed the gauge in the conventional BV formulation, that is that remove the Gauss number restriction and take the Siegel-Ramon gauge defined by these two conditions. And Hilbert space satisfying these two conditions, we denote it that restricted Hilbert space sub S Siegel-Ramon. Okay, and the cross tree-levelized matrix or tree-levelized matrix generating function can be written in this form, which is first derived. This formula is first derived by Zwiebach and Lee, and S phi 0 is a homogeneous solution satisfaction is obtained by the inputting that the phi classical phi 0, inserting that the classical action. The phi classical phi 0 is a classical solution determined as a function of the homogeneous solution, free field phi 0, obtained as follows. First, we note that the equation of motion, the gauge fixed equation of motion can be rewritten, which is a differential equation, but we can rewrite it to the integral equation in this form. Here, the phi is the phi, the string field, and the phi 0 is that free field, asymptotic states or something like that. And Q plus is that the integral operation, this like a bosonic propagator with some off-shell projection. The P0 is that the projection operator onto the on-shell sub is defined by the space satisfying this free field equation motion. This Q plus satisfying this relation is called in the mathematics called that the contracting homotopy operator. Okay, then this equation, integral equation, can be solved in closed form by using the coalgebra representation as function of the free field phi, homogeneous solution phi 0, in this form, where both phase A operators acting on the symmetrized tensor algebra defined by these relations, this definition, that they satisfy this uplift of these relations to the tensor operator acting on the tensor algebra. And then putting this phi classical phi 0 to the action, classical action I, we obtain the three-level S matrix generating function. And it is here we also use the again. Okay, we express the two-level S matrix by using the multilinear map introduced before. We denote this bra S is equal to this using that this capital symplectic form capital omega, using that and define that S operator here defined by this this definition. Which note that this provides a total S matrix in the BRT formulation, which means that they including the physical state and physical on-shell state. And this is also, now today I explained that this derivation follows by some physical literature, but it is also obtained by using that so-called homotopy perturbation theory, homological perturbation theory. Which already given yesterday's talks, and but I don't mention it here more. Okay, and this is the total S matrix. So the physical S matrix obtained by further projecting it to the physical subspace. Obtained by projecting that the on-shell Hilbert space to the physical subspace defined by the Q tilde cohomology. Q tilde is that BRC operator without all the Gauss Zelman. Okay, and the unitarity of this physical S matrix is guaranteed by this S operator is commutative with the BRC operator, which we can show, but we don't mention it today here in detail. Okay, the S matrix operator here.
8 minutes.
Okay, the S matrix element is further expanded with of course, the number of the external states and the number of the further the external Raman state. For example, the four-string scattering element at the three components. The first is that cyclic Raman number 0, it means that 4 Nobuyuki scattering and 2 Nobuyuki 2 Raman scattering and 4 Raman scattering. Okay. And okay, so now we have a closed form of the S matrix. So the next we have to show that it actually reproduces that conventional S matrix obtained in the first quantized formulation. Okay, so first we rewrite it. We use that the properties of the B operator, string product B, which is defined in the large Hilbert space. We rewrite this form to use that simplex form in the large Hilbert space here, and also define the sigma operator instead of the S operator. And using this the primitive operator B, which we first constructed, this sigma operator can be written in this form. This is a kind of Dyson-Schwinger equation, and the right-hand side, in the sigma in the right-hand side, with a large external states do not contribute in the right-hand side, we can recursively determine this sigma n plus 2 from starting from the sigma 2. It's just a fit B2 itself. Then we extend this to the two-parameter extension, this Dyson-Schwinger equation by extending the B to the BST, which is introduced first, and also that the factor here in the right-hand side to also to the some ST. This form of delta is data that Q sigma so the Q is in extension by extension. So that the sigma is reduced 1 at the equal to 0 and some that is that the derivative is T derivative will be it just it can
Have we lost?
It looks like you lost him.
Okay, it seems we lost him. Okay, we can wait for still a little while to see if he comes back online. So now is the question period starting. Hello, are you there, Hiroshi? I cannot hear him. Can anybody else hear him?
No. Hiroshi, your microphone, maybe you have to watch out. We can't hear you.
He has to unmute himself. He's not unmuted. He needs to unmute himself.
Yes, Hiroshi is muted.
Unmute. Okay. He has to unmute himself. You can't unmute him?
I can ask to unmute him. I clicked ask.
Okay, he's there. He should be there now.
Hello? Hiroshi, are you there?
can hear, but my
Okay, now we're hearing you again.
is lost.
Okay, so okay,
Can you hear me?
so we lost you a couple of minutes ago. So now we're already into the question session, so maybe you can wrap up.
Now can you hear me?
Yes, we
No.
can hear you. Can you hear us?
Yes.
Yes.
Okay, so now we're in the question session, so maybe you can wrap up quickly so we can ask you some questions.
Oh, so I quickly summarize my talk. Yeah, we can show that this S matrix extending S matrix. We can show that this S matrix, physical S matrix of the heterotic string is that just some inserting that the picture changing operator onto the external state, factoring out to the S matrix without inserting the picture changing operator and integrating out the whole model space, or in the field theory language that adapt all the possible Feynman diagram. So that is that now the position of the x0, we can freely move the x0 and just the S matrix, physical S matrix obtained in the agrees with the physical S matrix obtained in the first context method. Okay, this is summary, and okay, I should be stopped here. Thank you.
Okay, thank you. Are there any questions? Anybody want to raise their hand? Anybody? Okay, so one question. So you had on a previous slide, you had what looks like a minimal model for L-infinity algebras.
Yes. Not exactly minimal, but almost minimal.
Yeah, almost. Yeah, this almost minimal model. Or it's basically the formula for homotopy transfer.
Yes.
For an L-infinity algebra. So, yes. Have you checked did you just write this down, or have you checked that it's correct? That it's an L-infinity structure and cyclic and everything.
Yes.
You checked it, because I'm not sure that. Okay, I think that at least Martin Markle said that he has never tried to write it down for L-infinity, this homotopy transfer. So,
what point you are wondering?
What? Well, it's
what
just
point?
I think. Okay, I just wanted to be sure that that this formula is, you know, I'm not. I think it's probably trivial, but I'm not sure it's been discussed by mathematicians.
It is not. It is non-trivial. Yeah,
yes.
Quite non-trivial. But
yes.
we can prove that L-infinity algebra.
Yeah. So I think the fact that you're working on the symmetrized tensor algebra, the way that it will work out will be quite.
Yes.
Will be a little different.
Yes.
So, okay. So
yeah,
are
it
there
is quite non-trivial.
any other questions? I'm not seeing any other questions, so maybe we can move on to the next talk. Thank you, Hiroshi.
I'm sorry for my inconvenience.
It's okay. It was a nice talk. Okay. So our next speaker is Carlo. Are you there, Carlo?
Yes. Do you hear me?
Yes. Now I can hear you.
So I will show you my.
So Carlo will talk about classical solutions and background independence in open string field theory. Okay, so you can begin.
Okay, so Yeah, so thanks a lot for the opportunity to give this talk at this online conference. So I'm going to talk about this work that we did together with Ted about classical solutions in open string field theory. So first of all, why do we care about classical solutions in string field theory? So the string field theory equation of motion can give new handles on exact CFTs or boundary CFTs, which are not easily accessible from the standard CFT approach. Examples of these are, for example, the honeycombs equal to BCFT, which was discovered in level truncation by Kunitomo and Vosmera. And other example on different lines is, for example, the possibility to treat perturbatively Ramon backgrounds in RNS, as was discussed recently by Chocollier and In. Moreover, some backgrounds just don't have a direct CFT or boundary conformal field theory description sometimes. An example of this is the Tachyon condensate. And to study their physics, one needs field theory-like tools in general. On top of that, in any quantum field theory based on a path integral, classical solutions are the saddle points of the action, and they account for non-perturbative contributions to amplitudes. Therefore, if we want to have a non-perturbative understanding of string theory from string field theory, it is necessary to understand how string theory backgrounds appear as classical solutions, and therefore how background independence is implemented. So this is how background independence is considered to be implemented in string field theory. We generically start to construct a string field theory, and we can construct it on any given exact string background, which can be a CFT node or a boundary CFT node, depending whether we are using open string or closed strings or together, with a dynamical field variable, which we may call phi, nodes, and an action. Now, this action will have classical solution, we call psi star, and they represent other boundary, other consistent backgrounds, which can be either CFT star or boundary CFT star. So now I just expand my dynamical field and I write it as the background, my classical solution plus fluctuations, and I just look at the dynamics of the fluctuations around the solution. Then my action will split into two parts. The first part will be the classical contribution of the classical solution that will give the 1 over G over GS contribution in the path integral, the non-perturbative contribution. And the second part will just be the action for the fluctuations. Now, background independence means that this expanded action for the fluctuation and the action directly formulated on the new background. So this new background is just another exact string background, so I can also construct directly a string theory on this background. So these two theories should be related by field redefinition. By this, I mean that there exists a map F that takes the degrees of freedom of the target BCFT or CFT, BCFT star, and map them to the degrees of freedom of the initial background BCFT node. And if I plug this field redefinition into the action for the fluctuations around the classical solution, I should find a consistent string field theory directly defined on the background BCFT star. And let me also mention that in doing this, of course, a Jacobian is generated in the field redefinition, for the field redefinition in the path integral measure, but this is a quantum effect and we will not consider it here. So from now on, we will focus on classical, weak, and bosonic open string field theory, which, as of you well known, this has this form. It has this kinetic term and this simple cubic interaction term. So phi is my dynamical variable, and it's just an open string that is attached to a D-brane that is my given initial background BCFT node. So this theory has a well-known cubic quadratic equation of motion, and a class of solutions for this equation of motion was discussed by Ted Erler and myself in 2014 and later upgraded in 2019. And this class of solutions, we call them intertwining solutions, and has this form. It is built with two terms. The first term is just the Tachyon vacuum. So I'm originally considering my open string field theory defined on this initial D-brane system. I condense my initial D-brane, and then when I am at the Tachyon vacuum, I consider a new soliton that creates me a new D-brane system, the CFT star. And this is done by the second part of the solution. Now you see the second part of the solution has three ingredients. One is just the Tachyon vacuum in the target BCFT. So that's just a solution of the open string field theory defined here. But these two states cannot talk to each other, right? Because they live in different Hilbert space. So you need some intertwiners. And these intertwiners are provided by sigma and sigma bar. So this sigma and sigma bar lives in the space of strings between BCFT naught and BCFT star. And okay, I can take this answer, plug it into the equation of motion, and I find that these intertwining fields should be killed by the kinetic operator at the Tachyon vacuum. And moreover, they should satisfy this property, that sigma bar sigma is equal to 1. So in our construction, we have that sigma bar sigma is equal to 1. We will give it for granted, and later on we will see how we can realize explicitly this property. But once sigma bar sigma is equal to 1, then sigma sigma bar must be must be a projector. And this projector, just by matching the degrees of freedom, lives in the original Hilbert space BCFT naught. So in full generality, since the equation of motion don't fix the form of sigma sigma bar, we will just have to assume that there exists this projector in our initial BCFT naught, and we will see that this projector will have an interesting role in the proof of background independence. There are other important properties which descend from the previous ones. The first one is that if we consider the kinetic operator around the solution, and we act it on the fluctuations of this form that are taken from the target BCFT and then are intertwined to live in BCFT node by the sigma and sigma bar, then somehow magically this kinetic operator around the solution passes through the intertwining field and transforms itself into the worldsheet BRST charge in the new background directly. And something very similar happens at the level of correlators. If I compute correlators in my starting background of states that have this form, then essentially I can take this sigma and do simplicity of the trace, and then I end up with a correlator directly defined in BCFT star. So these are properties that we have been able to check in explicit examples. So let's go quickly on observables. Just by the form of the solution, it's pretty immediate to show that the solution has a consistent action, in the sense that the action directly reproduces the shift in the G function of the two-boundary conformal field theory as expected. And moreover, the coupling of the solution with on-shell closed strings correctly reproduces the shift in the clustering tadpoles between the two backgrounds. Therefore, the solution reproduces the correct boundary state of BCFT star. Now we go to the more important point. This is the point of background independence. So as we said before, we take our dynamical variable and we write it as the solution plus a fluctuation around the solution. But now we remember that we have this projector at hand that lives in our original Hilbert space, and therefore it makes sense to decompose this fluctuation according to the eigenspaces of this projector and its complement 1 minus p. So if we do this, then essentially we unpackage our original fluctuation in 4 sectors that can be assembled in a sort of matrix that looks like a Champaton matrix, but it should not be confused, because it's not really a Champaton matrix, because that's just a way of writing the initial fluctuation. In fact, in this matrix, every entry is constrained to live in linear subspaces of the original space. This should not happen in a normal Champaton matrix. Okay, but given this detail, which is quite important though, we can simply now consider a one-to-one field redefinition to a new set of variables that are these new variables here. And in particular, there is this phi 11 star, which is precisely the expected new variable of the new background BCFT star, which is unconstrained, because this 1, 1 means here essentially that there is 1 and 1 here. And there are these other 3 variables, chi, bar, and t, which on the other end are constrained and lives in the corresponding Hilbert spaces. Now, the nice thing is that this field definition is invertible if we keep track of these projector conditions, and we can also write the inverse without too many difficulty. So if we now plug this field definition into the expanded action, we get, of course, the correct constant part of the action, and we get also what we would like to get, that is the theory directly formulated in the new background. This is just open string field theory defined on all this BCFT star. But in addition to this, we also get this other sector from these other constrained variables. The nice thing is that this other sector arrange itself into tachyon vacuum fluctuations. So that's a theory of the tachyon vacuum. It's not the most generic theory of the tachyon vacuum because these fluctuations are constrained by these linear constraints, okay? So this thing was first discovered by Kishimoto, Masuda, and Takashi for our first edition of the solution, where this projector was not really defined in a consistent way. But so now this construction is more solid, and we can take it seriously to go on. So now we just have to consider that the only perturbative solution around the tachyon vacuum is chi equal to chi bar equal to t is equal to 0. Okay. Therefore, in the perturbative expansion around the saddle, which is what I'm supposed to do, the tachyon vacuum sector can be just integrated out, setting it to 0, and the action of the physical fluctuation phi star does not change. This is very important, and this is very different from the integration out of the massive fields that we have observed, that we have seen in previous talks in this conference. And one of the reasons for this is that QTV has no cohomology. Therefore, when we integrate this sector out, nothing is left. Moreover, amplitudes in the background of the solution are mapped to amplitudes in the new BCFT background very easily. So how have we achieved the background independence? We have achieved it in a three-step process. The first two steps were the expected one, the shift and the theory definition. But then there is this integration out of trivial fields, which is really something genuinely new. So we could ask, the constraint tachyon vacuum sector would be absent if sigma sigma bar would be just 1. So can this just be possible? So on general ground, if also sigma sigma bar is equal to 1, then in this case, the cohomologies of the two backgrounds would be strictly isomorphic. But this is something that we don't expect in general to hold, except for some special exactly marginal deformations. Therefore, physically, sigma sigma bar different from 1 is there precisely to allow to connect genuinely different backgrounds. And moreover, gauge equivalence in the original Hilbert space implies gauge equivalence in the final Hilbert space and vice versa. And this extra pure gauge tachyon vacuum sector is there precisely to account for that. So now it's time to explicitly realize our construction. A tachyon vacuum solution is available very easily in the KBC algebra. So we just have to construct the sigma and sigma bar. As I was telling you, sigma and sigma bar must be killed by QTV. Therefore, they must be QTV of something, because in QTV there is no homology. And we can build them in this form using known ingredients, new ingredients that are these flag states that I depicted in red, sigma and sigma bar. So sigma is the flag and sigma bar is the anti-flag. And just by algebraic consideration, they have to satisfy this constraint here. So how do we realize them? We can realize them, these flags, as surface states with boundary condition changing insertions. So here I depicted them in the sliver frame. So you see that, so the midpoint of the string is up ahead here at imaginary infinity. So close to the midpoint, this flag state just looks like the identity string field, but close to the endpoint, you have some space to glue some non-degenerate local coordinate where you can put, where you can insert a boundary condition changing operator. And the same you can do on sigma bar. Now it is possible to map the surfaces obtained by gluing flags and wedge states to the upper plane using Schwarz-Christoffel maps. So now if we multiply an anti-flag with a flag, very easily we can see that essentially here we get some open string degeneration, and there is a 2-point function that pinches off of the worksheet. So we are left with this 2-point function of sigma and sigma bar that can be just set to 1 by normalizing appropriately the boundary condition changing operator. And here the identity string field in BCFT in BCFT star. So we realize this important property. If we multiply them in the other sense, now there will be no more open string degeneration. We will just get a new surface state. This new surface state, of course, must be a projector. And this is a very interesting new projector that was not known before. So this looks like the identity string field towards the midpoint, but it has a non-degenerate boundary here, and it is left factorized towards the endpoint. So towards the endpoint, it looks like more like projectors that were studied in the past, like the sliver or the button. So we can also very easily construct multi-brane solutions, just taking multiple flags and asking them to be orthogonal in this sense. So this orthogonality condition is easy to achieve because we can just choose boundary condition changing operators that are orthogonal in the sense of the of the metric defined by the 2-point function. And moreover, we can consider universal multibranes. We just have to take these sigmas to live in the Maccaferri module of the identity, and then we can easily diagonalize the metrics of the inner products. So I think it's worth make a comment on non-perturbative amplitudes, because this multibrane solution can be used to account for multi-d-instanton contribution to closed string scattering amplitudes in two-dimensional string theory, following the work of Baltazar, Rodriguez, and more recently by Sen. This can be done using Elwood invariants and open string propagators, using the fact that width and vertex cover all bosonic moduli space. And therefore, we will have to deal in general with open-closed amplitudes of the kind that were discussed yesterday by Yuji and also by Harold, and more of it we will hear in the next talk by Jakub. Integration on the moduli space of the d-instanton will be carried over by the open string path integral, as Ashok was explaining us in his lectures last week. So the idea is that you can just define your open string field theory on a 1D instanton in this way, and you can compute all the perturbative contribution from the 1D instanton background, but then you can switch on your classical solution that we just saw, and you can go to a 2D instanton background, and so forth. You can go to a 3D instanton background, and you will have all of these amplitudes contained in the path integral of the same theory. Now, it's a bit puzzling how to get the 0 instanton sector. That should be the real perturbative contribution in this sense, but there is a natural candidate for this, because this should just be the Tachyon vacuum. And you could consider scattering of Elwood invariants at the Tachyon vacuum, and this should give you purely closed string amplitudes, as was already discussed in the past during the time of vacuum string field theory by Gaiotto, Rastelli, and Zwiebach. So we can have this. So I think that since bosonic two-dimensional string theory makes sense at the quantum level, this is a very concrete arena to test both the solutions and the possibility that open string field theory could be sort of consistent theory at the quantum level. So this is how we, just a technical slide on how we realize the Schwarz-Christoffel map for computing correlators of this form. I think I can quickly go over. And but essentially, this is needed to really go inside the solution and to see what are its coefficients in terms of the space-time fields that are excited by the solution. So the coefficients of the solution are in general given by a product of two quantities. K is a universal function which depends on the choice of Tachyon vacuum and on the details of the Schwarz-Christoffel map. And Ci sigma sigma bar is a basic 3-point function that is the only physical data that is really needed to define this solution. That is the 3-point function between the sigma sigma bar, the BCC operator, boundary condition changing operator that defines the solution, and the test state of my starting background BCFT node. So if we have these two, so this thing can be computed with the Schwarz-Christoffel map. This thing comes from conformal field theory, of course. So we have analyzed a ghost number 0 toy model. We would have liked to analyze the full solution, but unfortunately, to analyze the full solution at ghost number 1, we would have need a 7-dimensional integral on an implicitly defined region by the Schwarz-Christoffel map to compute this K. So on the other hand, in the toy model, we just need 3 integrals that are essentially the Schwinger parameters of these 3 functions of K. And so this was more doable, and we did it. And so we can take an example just to see some particular example about the Cosh rolling tachyon. So one of the advantages of this solution is the possibility to describe time-dependent background, just as any other background. So in particular, we can have a look at the Ashok's rolling tachyon boundary conformal field theory. So this is an exactly marginal deformation of initial Neumann boundary condition for the time-like free boson X naught. It's done in this way. So lambda is the marginal parameter. So a boundary interaction of this form can be replaced by a pair of boundary condition changing operator, as usual. And this boundary interaction is a periodic moduli space. It's known that is in the interval 0, 1. When lambda is equal to 0, we have no deformation. So we have Neumann boundary conditions for our perturbative vacuum, X naught. So for our X naught, this is just the perturbative vacuum. At lambda equal 1/2, we end up having multiple Dirichlet boundary condition at imaginary values of X naught, which are 2 pi I n plus 1/2. So this information is just taken from the fact that if we weak rotate to Euclidean signature, Cosh becomes cos, and it is very well known that at lambda equal 1/2, the cos deformation develop an infinite array of lower dimensional D-branes. Moreover, the boundary state can be computed and is shown to vanish for real time at lambda equal 1/2, although this Dirichlet boundary condition in imaginary time still gives some non-trivial support in imaginary time, okay? So in a sense, it is quite natural to expect that this lambda equal 1/2 should correspond to the Tachyon vacuum because the brain essentially has disappeared at lambda equal 1/2. So we can just look what our solution has to say about that. Hello? Oh yes, okay, sorry. So we can have a look and we can compute the Tachyon profile. We can compute this Tachyon profile in the usual way, just contracting the solution with the test state made of weak rotated plane waves. And to do this, okay, we have to do some numerical integration on this region given by the Schwarzschild-Stoffel map. But more importantly, we need the physical ingredient, which is the 3-point function of the boundary condition changing operator of the Cosh deformation with this e to the n x naught. So this 3-point function was not known in the literature. No one ever I think discussed really the boundary condition changing operator even of the Cosh deformation. So we had to do it by ourselves. And we ended up computing this 3-point function in this compact way. These are polynomials. So this is, I would say, this is a new CFT result by itself. And it's quite compact and it's useful for this particular example. So if we do this, then we can plot the Tachyon profiles that we get for this rolling Tachyon solution. So when lambda is very close to 0, indeed the Tachyon stays at the perturbative vacuum here for quite large time, and then there are these very wild oscillations for late times. This is quite common in these rolling Tachyon processes when they are seen from an open string perspective. So when you go to lambda equal 1/2, on the other end, we see that the profile doesn't change really dramatically. At the lambda equal 1/2, we were more or less expecting to get the Tachyon vacuum. The Tachyon vacuum would just be a straight line, horizontal line at 1. Okay, because in our toy model, Tachyon vacuum is just the identity string field. So this is not what happened. Okay, so that's somehow unexpected. But moreover, I think there is a more physical reason why this may not be the Tachyon vacuum, and the fact is that we have approached this point with a marginal deformation, and this marginal current, therefore, would be a physical state at the Tachyon vacuum, which is not something that we expect to be there at the Tachyon vacuum. In fact, when lambda is equal 1/2, a new branch of modular space opens up, allowing to translate these imaginary branes in imaginary time. This was discussed a long time ago also by Gaiotto, Zaki, and Rastelli. And so therefore, so according to them, the Tachyon vacuum should correspond to pushing these branes at imaginary infinity. So this is a picture of the modular space. So we start here, we go to lambda equal 1/2, and then there is this new branch of modular space that allows to separate the d-branes in imaginary time, and I can push them far away to infinity. So we can follow, with our solution, we can also follow this part of the marginal flow, and this is what we get. So we can essentially move these d-branes in imaginary time from these positions to generic position parameterized by A, and this is what we get. You see that when we increase A, now the Tachyon profile gets flatter and flatter and gets localized to its Tachyon vacuum value 1. So therefore, from this viewpoint of just looking at the Tachyon coefficient, this would support the idea that indeed the Tachyon vacuum is only found after you push these d-branes in imaginary time. Now it's important to notice that all of these backgrounds from the open string field theory perspective, they are all different. They are not related by gauge transformation. So they are genuinely different background. But on the other hand, they all have a vanishing boundary state, okay, because the boundary state all vanishes in real time for the same reason as the boundary state for lambda equal 1/2 vanishes. So I think this is quite interesting things to understand better. So let me go now to the conclusion. So for the first time, we have a non-perturbative realization of background independence in open bosonic string field theory. And we would like to use this solution to account for non-perturbative contributions when the bosonic string makes sense at the quantum level. Of course, also we would like to better understand time-dependent backgrounds with vanishing boundary state in open string field theory. So this should correspond to closed string radiation expressed in open string variables. I think now we have a quite concrete apparatus to really study this thing concretely. And of course, it would be very desirable to to have a similar solution for open superstring field theory. This would give, for example, a field theory understanding of the Ramon-Ramon charge. It would help us in understanding instanton contribution. It should be mentioned that as of now, we have the solution for cubic superstring field theory at picture 0, and we will hear something about this in future talk by Ruggero Noris. And okay, that's kind of wishful thinking, but of course, ideally, we would like to have, we would like to be able to connect also closed string backgrounds in a similar way. So thank you for your attention.
Okay. Okay, thank you for your talk, Carlo. So you now have 4 minutes for questions.
Okay.
So are there any questions from anyone? Okay, from Ivo.
Yeah, hi. Thank you for the talk.
Hi, Ivo.
Yeah, the question I had is, when you have these deformations of an open string background, you know, which gives you new boundary conformal field theory, how does the open string field theory know about the Cardi condition that this is satisfied?
That's a quite interesting question. I think the answer lies in the fact that your original background is already consistent, so it satisfies the Cardi condition. And I think the answer to this question is contained in the paper by Barton, Okawa, and Kiermaier, KUZ, where they constructed the boundary state from open string field theory. And essentially in their construction, the Cardi conditions are built in. If you look at their paper, you will see that essentially their boundary state satisfies by construction the Cardi conditions.
I see.
So it's the consistency of the initial background that assures that everything else is consistent.
All right, thanks.
Okay, we have another question from Muhab.
Yeah, hi, Carlo.
Hi.
I have an elementary question about the energy. Can you compute the energy for this rolling tachyon solution, and can you follow it as a function of time and perhaps see that either it goes to 0 or then it goes into imaginary values? Maybe that would be a way of understanding the physics of what's going on.
Yes, so I think that so you can compute the boundary state, and you will just get the value that is well known from boundary conformal field theory. So so I think in this sense you will find the 0 energy, but still it's a kind of a time-dependent background, which is not so clear.
No, I think it should be a time-dependent. I mean, the energy should be a function of x naught.
Yeah. The energy is not conserved, of course. Yes.
So,
yes.
And then it's a function of time, and then of course there's radiation. It goes away, and the question is whether when you reach lambda is a half, which is the thing that you would like, the value which you would like to associate with the tachyon vacuum, whether then this function reaches 0.
Yeah.
What function? The energy?
The energy as a function of x naught.
Energy
Right?
is
I mean,
So it's just the 0 component of the boundary state. It's just so.
the energy momentum tensor?
Yes, I mean this is a background. It has fields. It carries some energy, and it's a time-dependent background. So the energy that it carries is a function of time. So the question is whether we can find it.
The closed string background is time independent. So the
energy is conserved, I think.
Energy of the open string field is conserved.
Yeah, I think Ashok can help us in answering this question.
I think energy is conserved. It's just 0. I mean, for this solution, it's just 0.
Yeah.
All the way throughout?
For lambda equal 1/2, the energy is 0, right?
Yeah. Because it's rolling in a time-independent closed string background, right? So there is a time translation invariance.
Yes.
So energy is conserved all through.
But I thought as an open string, it was dependent on x naught. As an open string background, it was dependent on x naught, so it was time dependent.
Yeah, the solution is time dependent, but energy is a conserved quantity, right? So that's why it's conserved. It's constant all along the motion. See, the pressure changes. The pressure changes as a function of time, but not the energy.
I see. I see. So it's just right. So it's distributed in a different way over the fields as time evolves.
Exactly. Yeah. It may get redistributed among various fields, but it's constant. The total energy is constant.
All right. Thank you.
Okay, I think that's all the time we have for questions on this talk. So I think our next talk will be, okay, who's coming next? Jakub. Are you there, Jakub?
Yes, can you hear me?
Yes, I can hear you.
Perfect.
So go ahead. Okay, new results on localizing string field theory effective actions.
Okay. Okay, can you see my slides?
Yes.
Okay, perfect. Okay, thank you, Ted, for the introduction. Also, I would like to thank the organizers for giving me the opportunity to give yet another talk involving effective actions, multiple transfer, and all this stuff, which was already extensively discussed both today and yesterday by many speakers. So, in the first part of the talk, I would be speaking about generalizing the story of T-level bosonic OSFT effective action modified by adding a gauge invariant forcing to the case of open superstring field theory. So this is a story which we already heard yesterday by both Yuji and also Harold. I will also focus on actually trying to evaluate some of the leading order corresponding tree-level on-shell open-closed amplitudes, so that we have actually explicit expressions for the vertices of the effective action in certain special situations. And in the second part of the talk, which should be roughly a last quarter of the talk, I will focus on computing tree-level quartic effective potential in heterotic Young-Mills from heterotic SFT. And in particular, I will show that it's actually possible to reproduce an algebraic coupling for heterotic Young-Mills in 10D flat space at quartic order without actually having to know the explicit form for the closed string bosonic quartic vertex. So let me start with the first part of the talk. So here I will generally use formulations of string field theory using a cyclic infinity structure. So here we can see the action written manifestly in a cyclic infinity form. So for introduction, you should refer to yesterday's talk by Hiroshi. The same action can be neatly rewritten using the so-called tensor algebra language. So that was already introduced to you yesterday by both Yuji and Harold. So here, this fig M is a coderivation which encodes all the infinity or the cyclic infinity products which are used to define the theory. So in this language, we can express the gauge transformation connected to this action in this form. So see, for instance, this paper by Ted, where this explicit form for the gauge transformation appears, and it is then actually it is then easy to see that if we define a quantity, which I denote by curly E, in the following way, using an odd cyclic coderivation E, then this quantity is gauge invariant, possibly up to pieces which vanish on shell, that is up to trivial gauge transformations, whenever this coderivation E commutes with this coderivation M, which encodes the products of the theory. So this is a thing to remember, because we were going to encounter this a lot on the following slides. So in the following 4 slides, I would like to give you a short reminder of what was already discussed yesterday by both Yuji and Harold. So in particular, I will discuss the cubic open string field theory, which is deformed by adding the so-called Elwood invariant. So this is precisely the stateful part of the action. Here mu is an arbitrary number, which will keep track of which will basically keep track of the number of co-string insertions, as we will see on the following slides. Here, E naught, this is important, is given by a closed string primary state inserted at a midpoint, at the open string midpoint on the identity string field. The closed string primary state needs to be on shell, so this gives you a gauge invariant quantity, which was first given by Hashimoto and Etsaki, and also independently by Gayoto, Rastoisa, and Zwiebach. So this same action can be then rewritten in tensorial algebra language in the following way. Here, so by the way, I forgot to say, so although it may not appear that way, so this letter is really a capital S written in Gothic font. So in the same way, I'm now going to introduce co-derivation Gothic M, which encodes the products of this mu deformed action. So here E is a co-derivation, which is just defined using this midpoint insertion E naught. And by virtue of E naught being on shell, and also by virtue of it being inserted on the midpoint, we have the following properties satisfied by the co-derivations M and E. So in particular, it follows that if we then go and square this co-derivation Gothic M mu, we get a 0, right? Because order by order in mu, first we know that M squared is 0 because we have basically an A2 structure. Then we get a 0 at linear order M mu because M and E commute with each other. So this fact that that M and E commute with each other is already telling us that we're dealing with a gauge invariant quantity. And as we saw on the previous slide, and also we have this property that E squared is 0. So in total, this gives us that this Gothic M squared is 0, which, as was already pointed out yesterday by Yuji, gives us a kind of a trivial instance of weak infinity structure. So now let's talk about deriving trivial effective actions for such an SFT. So in particular, I'll be interested in the effective action for the modes which reside in the kernel of L0. So P node will be my projector on the kernel of L0, which I'm going to a little bit artificially split into canonical inclusion and canonical projection on P node H. H is my Hilbert space. So in the second step, after I split the string field using this projector, I'm going to integrate out the massive modes using a Siegel gauge propagator, which is defined in this way. So here note that I have a relative minus sign with respect to UG. So such a propagator satisfies together with Q and the projector the so-called Hodge-Kodaira decomposition plus the so-called annihilation conditions. So altogether, I can observe that I obtain an algebraic structure which is called a strong deformation retroact, as was already pointed out by both Harold and also Hiroshi yesterday. So in the case that I just turn off the mu deformation, so I just have a pure cubic action, the effective products are given by the so-called homotopy transfer, which can be written in this way. Here, phi tilde and I tilde are cohomorphisms, are perturbed cohomorphisms, which are defined using the corresponding cohomorphisms I and pi, which corresponds to the natural inclusion and projection, basically by virtue of the homological perturbation lemma. So here I'm perturbing my original structure by adding the star product M2. I can then, of course, just unpackage this co-derivation M tilde and derive the actual products of the effective theory. So here, for instance, we have the effective free string product, which was already reported by Hiroshi Kajura back in 2001. We can also show that given the BPZ properties of the propagator, the effective products are cyclic with respect to the projected simplex form. Using an analogous formula, which I used to define the homotopy transfer for the effective products, I can also investigate what I get by doing a homotopy transfer for this coderivation E. And it turns out that the resulting coderivation E tilde commutes with the effective products M tilde. So what I obtain is a gauge invariant quantity for the effective SFT given by this expression. So then, of course, I should be interested in what happens in the case where I turn on this mu deformation by the Elwood invariant. So, the first thing I notice is that it is not enough to deform the effective products by this effective E tilde coderivation. Instead, what happens, I need to also add contributions which contain higher powers in closed string insertions, and this is basically because when I just add this E tilde to M tilde, it no longer squares to 0, essentially because E tilde doesn't square to 0. So that tells me that I need to really do more complicated deformation, which is nonlinear in E. So by the way, this formula is completely equivalent to a more compact formula which was given to you yesterday by Yuji. So then, of course, I can again unpackage and express really these mu deformed effective products in terms of the undeformed effective products and also the propagators. So one aspect which was not really discussed yesterday is the fact that this mu deformed action both on the UV and IR effective level actually contains a tadpole. So that means that we are not expanding around the true vacuum of the theory. So in order to restore a canonical infinity form for the action, I need to perform a vacuum shift. So in Siegel gauge, solution for the vacuum shift can be given as follows. Here I also included possible corrections at each order in kernel well not. And an interesting fact is that this vacuum shift can in general be obstructed. So these are the obstructions to the vacuum shift. And this is a sign of the BCFT, of the underlying BCFT being unable to adapt to this new deformation. So in the coalgebra language, I can express the vacuum shift in a closed form as follows. So here I packaged all these order by order corrections into the string field little psi p. So, and I use the string field to express both the vacuum shift of the full SFT as well as the obstructions. And I can immediately see is that that a nice interpretation for these corrections is that they basically determine the true vacuum of the effective SFT, and the obstructions to the vacuum shift of the full SFT precisely coincide with the equations of motion for this vacuum shift of the effective SFT. So in most examples which we encountered, we have that these corrections can be set to 0. So in these cases, the obstructions precisely determine the tadpole part of the effective action. So yeah, so this much for the review of what we've already basically heard yesterday. So now I would like to speak about how to generalize this story to the case of open superstring field theory. So in order to maintain algebraic continuity of the story from yesterday, I will choose to do so in the context of the Munich infinity open superstring field theory. So this is the action of this theory given in terms of the superstring products, again encoded by means of coderivation capital M. So these superstring products can be defined in terms of the bosonic products, which is just the BRST operator and the star product, recursively in the following way. And just by looking at this definition, it's easy to see that basically everything which is involved in this expression is cyclic with respect to the symplectic form, both in the small Hilbert space, in the case of small Hilbert space product, and in the large Hilbert space. So these mu's are the so-called gauge products. This whole construction can be neatly expressed in terms of these generating functions. So we kind of already met version of these generating functions in the talk by Hiroshi Kunitomo, but that was for the heterotic L-infinity version of the story. So these generating functions satisfy the following differential equations, which can then be used to show that the resulting superstring products are indeed infinity products and that they are indeed in the small Hilbert space. So solving these differential equations, we can then obtain the following relation, where we have introduced this cohomorphism G, which can be shown to be cyclic. So now, of course, if we want to repeat the story of the Elwood invariant from the cubic bosonic string field theory, we need to define an appropriate Elwood invariant for the infinity version of the superstring field theory. So unfortunately, I do not have time to really motivate this construction, but can be shown that if we define a product E0 by just basically again a non-shell bulk primary field insertion at the open string midpoint, this time in picture -1, and then we define recursively higher products E1, E2, E3, etc. using this recursion relation. We can show by again forming appropriate generating functions that the coderivation capital E, which is just given by summing all these E0, E1, E2, etc., satisfy the following properties, namely that it commutes with the superstring products, and also that it's clashed to 0, and as well that is also in the small Hilbert space. Also, it is manifest by the construction that E is cyclic. We can also solve the corresponding differential equation for the generating function for E to obtain the following expression in terms of the cohomorphism G. And we can then, of course, look at the corresponding gauge invariant quantity for the infinity superstring field theory. And by short calculation, we can see that it's related to the T Elwood invariant of the WZW-like superstring field theory by using the field thread definition introduced by Ted, Yuji, and Takazaki back in 2015. So if we then go and deform the Munich SFT by this Elwood invariant, then the story is exactly parallel to the bosonic case, with the difference is that now we have higher products for in the case of both M and E. So by the way, this really works by virtue of E satisfying the commutation relation with M, and also by virtue of E squaring to 0. So we obtain the special weak infinity structure, Gothic MU. And yeah, as I was saying, the story is exactly parallel to the bosonic case. So at mu equals 0, we define the corresponding cyclic infinity effective structure by the homotopy transfer, this time using the homotopy equivalence that are perturbed by the interactions of the infinity SFT. And again, if we turn on the mu deformation, we see that at the effective level, it is not enough to add the effective coderivation E. We also need to add a bit which is nonlinear in E. And again, we need to perform the corresponding vacuum shift in order to restore a canonical infinity structure which doesn't contain a zero string product. So the corresponding effective action can be expressed using the coderivation Gothic M tilde in the following way. We can kind of reorganize this effective action by means of the following double expansion. So here, K plus 1 counts the number of open string insertions, whereas alpha counts the number of on-shell closed string insertions. So again, we can then extract the corresponding effective string products by the following way. So here I give you some expressions at low order. So first of all, here we obtain the tadpole part of the effective action. Then at order which is linear in both, which is quadratic in open string field and linear in a closed string, we obtain a mass shift for the states in our BCFT. Then here we have a cubic coupling, and finally here we have an effective quartic coupling, both at order mu to the 0. So let me now 5 minutes. Thank you. Let me now shortly discuss a way of explicitly computing some of the couplings in this action. So I will focus on the following form for the closed string state, and I will also focus on monoshell open string states in the following form. And from now on, I will also assume that the background which I choose admits a global n equal to vértice superconformal symmetry. And I will also assume, as I have already hinted at in these expressions, that both the open and closed string insertions will be at 0 momentum. So then I can decompose my matter fields in terms of eigenstates of the corresponding U1 R charge of the n equal to superconformal algebra. And this decomposition already guarantees that I have no effective cubic coupling, and also I have no effective tadpole. So in order to express higher order couplings, it turns out to be very convenient to introduce the following auxiliary fields, in terms of which I can express by using the results of Carlo and Alberto Meruano the quartic effective potential in the following way, and I can also express the mass shift in the following way. So here you can notice that I have no integrations over Bose-Einstein moduli. So these expressions turn out to be fully localized on the boundary of the worksheet moduli space, where the propagator turns into an infinitely long string. The leading order effective potential can be obtained by just assembling these results. It takes the following form. I can notice that it has a global minimum where the auxiliary fields satisfy these equations, and the depth of this minimum is given by these expressions in terms of the auxiliary field. So this basically gives me an effective tachyon potential for modes in kernel Bell node, which become relevant after turning on the mu deformation. So it describes the condensation of these modes into bound states, which has a mass effect given by this expression. So we can run an explicit example in the case of D-1 D3 system in the B field, and I can show that these expressions reproduce the normal results. So finally, let me just briefly go over a story of the heterotic SFT. So here we are in the large Hilbert space using the Berkowitz-Zwiebach action. So again, we are interested in an effective action for modes in the kernel of L naught. So when I focus on the physical modes in the kernel of L naught, I have either the usual physical fields for the heterotic string or the so-called ghost gelatin. And the effective action for the, at least up to the quartic order for the physical modes, can be shown to be, again, given by the familiar expression using the propagator. Here we are in the Siegel gauge. And I can also show that the unphysical fields in the kernel of L naught decouple up to quartic order. So again, if we want to compute the quartic coupling, we localize basically. So we assume that we have an equal to vértice superconformal algebra in the homomorphic sector of the heterotic string. I again decompose into the eigenstates of the U1 R charge of the n equal to symmetry. And analogously to the open string case, when I had vanishing cubic potential for the n equal to, I also have vanishing cubic potential in the heterotic case. And again, I can show that the quartic effective coupling localizes on the boundary of the vertical moduli space, where this time the propagator transfers from an infinite long tube. And this has a very good property that the fundamental bosonic quartic vertex basically drops out from the calculation. So in order to perform the computation of the quartic vertex of the effective action at zero momentum, I don't have to know the explicit form for the bosonic quartic vertex. So again, in order to actually give a final expression for the quartic coupling, I introduced the auxiliary field in terms of OPEs of the matter fields. And this is my final form for the leading order, that is quartic effective potential. So just to give you a concrete example, we computed this potential for Yang-Mills in a flat 10D space, and we have shown that we can reproduce the expected form for the quartic Yang-Mills potential at zero momentum. So finally, I leave you with a summary of my talk and also a couple of suggestions for future projects. Thank you.
Okay, so thank you for your talk. So are there any questions for Jakub? Okay, I had a question, but now I forget what it was. So I could ask you later. But oh, here, okay, there's a question from Ivo. So Ivo, go ahead.
Yeah, hi, Jakub, nice talk. So this is a naive question, sorry about this one, but so this Elwood invariant, I mean, what is really the difference between an Elwood invariant and the open-closed vertex?
So, so at least in the bosonic case, right? So it was shown by Barton Zwiebach back in 90s that the Elwood invariant can be obtained as a special limit of the full open-closed string field theory. So this is really a special case of the full open-closed coupling in the case when the closed string insertion goes on shell. So
okay, thanks.
So yeah, I'm not familiar with an analogous construction in the superstring case. So that's actually one of my suggestions for a future project.
All right, thank you.
Okay. Are there any other questions?
Yes, I have a naive question. So we have not seen the vertex in this construction. I mean, as something from the supermodular space. Should we
sorry, maybe can you repeat, because I didn't really understand the point of the question.
So
or
there's no construction of vertex.
Construction of
a vertex.
Oh, sorry, of what?
Vertex.
What?
I mean, from a supermodel.
Oh, vertex. Oh, vertex.
Yes. Yes.
Yeah, sorry. So from the point of supermodular space. Okay, I'm sorry. I don't think I'll be able to answer this question because I haven't really thought about this story from the point of view of supermoduli. I'm very sorry. Yeah.
What is your question again?
So there's no construction of vertex from this supermodel space of Riemann surfaces.
Well, I think Yuji Okawa and Omori, they discuss how you can understand superstring vertices from the supermoduli space point of view. And there's a few papers here and there, but I think that's something that there's still more to understand.
Okay.
Are there any other questions? Okay, so now we can take a break for 15 minutes. So when do we start again? Yes. So we start again at, okay, 3 minutes after 3:45. Okay, in 15 minutes. Okay. And okay, so I'll see you then. Okay, I think we can start the session again. Our next talk is going to be Nobuyuki Ishibashi, and he's going to talk about string field theory for non-critical strings revisited. So are you there, Nobuyuki?
Yeah. Okay. Can you hear me?
Yes.
Okay, so I'll share the screen.
Yes.
Yeah. Okay. Okay. I would like to thank the organizers for inviting me to give a talk here, and also for their effort to set up this online workshop. Okay, what I would like to talk about today is a very old subject, SFT for non-critical strings. And I will first talk about the motivation for doing so. So we are talking about string theory. So the world sheet is a Riemann surface. So there's a what is called hyperbolic metric on the world Riemann surface. There exists a metric with constant curvature if this condition is satisfied. And this condition with this, okay, so all the Riemann surfaces we need for string theory satisfies this condition. So this metric can be used for string theory. And of course, this metric was actually useful in studying string theory in 1980s. And there are lots of work done using this metric, using the mathematical results on this metric. So if it's useful in string theory, then this metric should be useful also in string field theory. But actually, string field theory with using, okay, so, we may not need any worldsheet metric to formulate string field theory, but if you have a definite metric, then it's good because you can do calculations more easily. So, hyperbolic metric is studied for a long time by mathematicians, and also there are lots of results in string theory itself, multi-loop calculation and so on. So this metric would be the most convenient choice for also for string field theory. But actually, this metric, as far as I know, this metric has not been used in string field theory until very recently. And because maybe the reason is because in order to construct string field theory, you have to decompose the surfaces into propagators and vertices. And it is not so complicated to get vertices with hyperbolic metric, but having propagators is a bit difficult. It's not so straightforward. But there are several new ideas recently, and on these things, I think the next speaker, Barton, will tell us about much. So I will not go into detail. And what I would like to do is something different. Okay, I would like to consider some construct string field theory with hyperbolic metric. But first, I will, what I would consider is first, actually there is a string theory with worldsheet whose worldsheet metric is fixed to be hyperbolic. And that is, okay, there's a string theory known as 2p minimal strings. This is just a all types non-critical strings in old days, and it is solved by old matrix models. And this is a string theory with 2p minimal models, CFT minimal model on the world sheet, and the Liouville theory, coupled to Liouville theory and ghost theory, ghost fields. And this is realized as a higher critical points of one matrix model. And of course, it's because it's realized by one matrix model, it is exactly solvable. And if you look at the Liouville action for this model, then it has the form like this. And there's a P in front of the whole action. So if you take the P goes to infinity limit and fix the cosmological constant to be 1, then the worldsheet metric is, it's a semi-classical limit. So the worldsheet metric is fixed to the solution to the classical equation of motion. And in this case, it's the constant curvature metric, that is hyperbolic metric. So in the limit P goes to infinity, this non-critical string has a worldsheet metric fixed to be the hyperbolic metric. And I should mention that recently there's a paper by Saad, Schenker, and Stanford. They have shown that this P infinity limit is equivalent to the topological gravity called JT gravity. And this JT gravity theory also fixes the worldsheet metric to be the hyperbolic metric. So we have string theory whose worldsheet metric is fixed to be the hyperbolic metric. So if we can construct a string field theory for this minimal string in the limit P goes to infinity, then we get an SFT for with hyperbolic metric on the worldsheet. So that means if you can do that, then you have somehow cut the Riemann surface into propagator and vertices with the hyperbolic metric on the worldsheet. So maybe if you can construct a string SFT for such string theories, then we can get insight into the how we can deal with the hyperbolic metric, how we can cut the surfaces in, cut the hyperbolic surfaces into propagator and vertices. So that's my motivation. So what I would like to do in this talk is to explain how we can construct string field theory for this minimal string. And actually, very long time ago, nearly 30 years ago, with Kawai and I constructed string field theory. I formulated string field theory for a minimal string in the case when P equals 3. And P equals 3 means the Virasoro central charge is 0, and that corresponds to the CFT with no field. I mean, there's only Liouville field on the and ghost field on the worldsheet. And for this minimal string, we can construct a string field theory. And actually, what I would like to show in this talk is it is possible to generalize this string SFT to a higher critical case. And also, we can take the limit P goes to infinity, and we get an SFT with hyperbolic metric. So outline of my talk is as follows. First, I will explain our work, my work with Kawai. That is a construction of SFT for C equals 0 string. And this string field theory is actually, the formulation is quite different from the usual one. and so I will explain the formulation and show that that formulation is quite looks quite like so-called stochastic quantization in ordinary quantum field theory. And then I will go on to the case. Okay, I will generalize this construction to the more higher critical points. And this part is actually very brief because it's quite technical. And then I will conclude. Okay, let me first explain how we can construct SFT for C equals 0 strings. And in order to construct SFT, we introduce a time coordinate, tau, on the world sheet. And okay, we have, okay, this is a non-critical string, so we have Liouville field on the world sheet, so we have metrics on the world sheet. So we can we can measure the distance between points on the world sheet. So we'll define time coordinate, which is for this. So okay, on the world sheet, for a point on the world sheet, point P on the world sheet, the tau coordinate of P is defined to be the distance from a P to the set of boundaries. So the minimum of the distance between P and Q, Q is a point on the boundary. So this is the distance between the boundary and the point P. So with this time, if you define this time tau, then the world sheet is arranged in this way. So okay, you take coordinate tau like this, axis of tau like this, then at time tau 0, there's a boundary. There are boundaries. These boundaries correspond to the external line in the string theory. And then, okay, this world sheet goes like this. And when tau goes big enough, then there's no world sheet. So eventually, this world sheet vanishes in a time evolution. So let's describe this time evolution using string field theory. Okay, now string, okay, we have only Liouville degrees of freedom on the world sheet, except for the ghost field. So the only degrees of freedom is metric, and only gauge invariant quantity for a string is its length. So everything can be, okay, so this string field can depend only on the length of it, of the closed string. So we introduce string field and its canonical conjugate. Or you can consider this as a creation operator of a string, and this as the annihilation operator, and also vacuum states. And these, okay, pi and phi satisfy this commutation relation. And pi is annihilation, so it annihilates the vacuum, and annihilates the ket vacuum. And the bra vacuum is annihilated by this creation operator. Then, okay, if you, with these setup, we can describe this world sheet by this expectation value. So at time 0, we have, in this figure, there are 3 strings. So okay, at time 0, we create these strings, and this is the state with n strings. Then it evolved in time. So the evolution of time time evolution operator is described by this operator H hat, which I will discuss it in the next slide. And when time goes on, eventually there's no string. So after enough time is passed, the bra vacuum should be there. So this world sheet can be described by this expectation value. So this will give the correlation function of these string fields. And so now what is this time evolution operator? And the time evolution operator can be given like this. And here, so they are expressed in terms of this creation and annihilation operator of string. And also here's W. W is the disk amplitude with boundary length L. Okay, let me explain each term in the Hamiltonian. So first, these two terms are usual three-string interaction. So if you look at this figure, then at this time, there are two strings merge. One string splits into two strings. So this such a process can be expressed by this term. Okay, this term annihilates one string and creates two strings. And and at this this time slice, we have two strings coming in, and they merge into one string. And this process is expressed by this one. These two are the usual joining and splitting interaction. Then comes on this term. Okay, eventually there's no string. When tau is big enough, there's no string. And so in the end, string should be annihilated. And so, for example, let's consider this time slice. There are two strings, and they merge, and then comes this disk. So we have two string annihilated and becomes disk. This is described by this term in the Hamiltonian. And then finally, there's a propagator. And the propagator is actually quite different from the we usually have in string field theory. And this propagator is of the form like this. This annihilates one string and create one string, but there's also a disk. So this process can be depicted by this process. And actually, with this Hamiltonian, we can, as I will discuss in the next section, with this Hamiltonian, this expectation value coincide with the correlation function of C = 0 string theory. The correlation functions, this coincide with the correlation functions calculated by the matrix model. And this, this is the string field theory we proposed in 90s. We means Kawai and I. And this is quite different from the usual string field theory. In 2 points. First of all, the propagator is a cylinder. Propagator is a cylinder, but perpetually bifurcating coordinates. So the Hamiltonian kinetic term of the Hamiltonian is of the form like this. So the string coordinates on the roll sheet bifurcate, and this happens at every time evolution. So this bifurcation occurs perpetually. And also another thing is that this form is quite, okay, very weird. This form of expectation value, this represents the correlation function, but this form is quite unfamiliar. But actually, this form is looks quite like what is so-called stochastic quantization in ordinary quantum field theory. So I will explain this stochastic quantization in the next section. Okay, stochastic.
About 5 minutes or 6 minutes.
6 minutes.
Yes.
Okay. Stochastic quantization is something invented by Parisi and Wu, and they showed that if you want to calculate the d-dimensional Euclidean field theory, correlation function of Euclidean field theory, then this can be calculated by using d plus one dimensional string field theory with one fixed time variable. And that this d plus one system is given like this. This is the same, okay, this one is quite similar to what I described for strings. So we consider the creation operator phi and the annihilation operator phi, and also vacuums, and with the Hamiltonian, which has this form. And so this system has a time variable in addition to the space-time coordinate x. So it is a d plus one dimensional system. And somehow there's a dimensional reduction from d plus one to d. And the reason why it happens is as follows. Okay, this system actually has a hidden supersymmetry, which is discovered by Gozzi. And okay, we can construct, introducing some fermionic coordinates, we can construct supercharges, and they form the superalgebra with this, okay, and this is the bosonic part of the super Hamiltonian. And this has us, okay, so because of this supersymmetry, actually this reduction occurs. And actually the string field theory we constructed is, okay, it has this form, and the Hamiltonians looks a bit different, but they can be expressed in, transformed into the following form. And this Hamiltonian looks a bit different from this one. And there's some so-called kernel in here. But, and these two, and this is actually a generalization of stochastic quantization, actually proposed back in the 80s. And this is called the Hamiltonian with kernel. And actually, so this is a kind of stochastic quantization. And because of this, the SFT Hamiltonian we have can be seen to be the correlation function is coincides with those coming from this action, which I will explain in the next slide. Okay, so SFT Hamiltonian I had has this form, and K is a kernel is of this form, and this so-called action satisfies this equation. And in principle, you can solve this equation and get the action, which can be considered as a string action for string field. And okay, we can derive the Schwinger-Dyson equation from this action. And that coincide, we can show that coincides with the loop equation of matrix model. And so because of this, okay, SFT results are equal to the correlation function of C equals 0 string theory. Okay, I will skip the some remarks. So that's what we had for two or three strings. And for two higher critical points, we don't, okay, we constructed the theory in 90s, and we all, of course, tried to construct SFT for higher critical points. But actually, it was very difficult because one reason, the reason for that is that the disk amplitude for higher critical points is more very singular for the for L very small. It behaves like this, and with P there. So if P is bigger than 3, this becomes very singular and make there are terms which involves P, W, and they become the integral becomes singular. And there was a proposal. Okay, a guy called Ikehara proposed a way to avoid this singularity, but it was not. His Hamiltonian is not good for taking P goes to infinity limit, which I want to have. And what I did was to this formulation, studying the formulation more carefully, and obtain a Hamiltonian for which this limit can be taken. And the answer is actually very simple. Okay, if we have the almost the same Hamiltonian, same form of the Hamiltonian, with this disk amplitude here, and actually this because this is more singular than P equals 3. This these integrals are not so well defined when for higher critical points, but there's a way to make it regular. So this R here denotes the sort of regularization. So there's a way to make it regular, and if you follow that way, then this Hamiltonian can be shown to describe higher critical points. And this, so this way is the method to make it regular is a bit technical, so I cannot discuss here. But anyway, this is so intuitively we have almost the same form of the Lagrange Hamiltonian.
So what
and
with
this, okay, and so and it's easy to take a P infinity limit, and we have the form of the Hamiltonian does not change. That's my conclusion. So what I've done is in this talk is as follows. We have constructed 2P SFT for 2P minimal string. And so that this string in the P goes to infinity limit is a string field theory with hyperbolic metric on it. So there's if you study it carefully, then you can see how we can divide the hyperbolic surfaces into propagator and vertices. But there are several peculiar points where this propagator is quite different from the usual ones. And also the formulation is stochastic quantization type formulation. Okay, maybe that's what I have to say. Thank you very much.
I forgot to unmute myself. Are there any questions for Nobuyuki? Okay, Yuji, we have a question from Yuji Okawa.
Yes, so when P is greater than 3, I thought the string field should depend on more variables than just the length. So are you considering a subset of string fields which close under the Schrödinger equation or something?
Yes, okay, when P greater than 3, there's a CFT degrees of freedom. But actually, on the other hand, when P goes to infinity, this should be equivalent to the JT gravity. So it somehow in the limit p goes to infinity that that CFT degrees of freedom somehow goes away. I don't know why, but it seems so. So I don't know. That may be an answer to your question.
Okay. We have one more question from Muhab.
Yeah, hi. Thanks for your talk. So I have a question about, well, first of all, taking this limit. So can you take this limit, P goes to infinity, and show that the field theory is JT gravity? Is it something you can check?
Yeah. JT, okay, JT, all the correlation, okay, JT gravity is equivalent to P goes to infinity limit of minimal string. That's what Saad et al. Showed. So, and also this, the string field theory I have okay, this gives the, okay, all the correlation functions, I mean, are included in this string field theory. So that means that these two are equivalent, including the observables. That's what I say.
Right. And so I guess, so for any value of P, whether P goes to infinity or not, this is a string theory, which is a field theory, not a string theory, right? So it's not a second quantized theory of strings. It's actually an ordinary two-dimensional quantum field theory.
Okay. There's no degrees of free. Okay, the degrees of
there are no stringy degrees of freedom, right?
Yeah, string. Okay, there's string field. Okay, but still there's a world sheet.
Right. So my question, no, but that's okay. I mean, there are string theories that are not string theories, that are field theories in this sense, right? I mean, but the question is whether you can relate this to any formulation of conventional formulation of string field theory. So some truncation, perhaps, of closed string field theory to the zero modes, which would give this particular field theory, if you see what I mean.
Okay. Okay. I don't. Okay. I don't know if there's any string field theory which describes. Okay.
Right. So it seems like you have truncated to a particular sector in which you only have field theory modes. So you don't have all of the higher modes that you have in the string. So this is really just a field theory. But the question is whether it can be understood, right? Whether it can be understood as a truncation.
Okay, I understand, but still it includes all the observables. This
no, I understand.
Okay.
I understand, but all of the observables are field theory ones.
Okay.
Right, they just zero mode. So it looks like a truncation from something which is much bigger, which is the ordinary, which is some string field theory of strings, which is truncated down to a field theory. But I don't know if you've thought about that.
Okay, I don't know the any bigger string field theory which describes this which is whose truncation becomes like this one. I don't know the any candidate.
Right.
Yeah, I think we have to keep going. So the next talk is Barton.
Yeah.
He's going to be talking about hyperbolic string vértices.
All right, very good. Thanks very much for the opportunity to speak at this conference. And so I will be speaking about hyperbolic string vértices. This is the plan of my talk. Brief introduction, talk about string vértices, the work of Musevian and Pius that motivated this, then some hyperbolic tools, hyperbolic vertices, Feynman region, Thurston metrics, open questions, and things like that. This is work that was done last year with Kevin Costello. There's been a nice paper by Minjai Cho following this and extending this to open-closed theory. So, very good. Let me give a brief introduction. It's probably not necessary here, but we have string field theories, and as you can appreciate, there's all two kinds of difficulties and challenges. One is algebraic, and the other is geometric, and both are necessary, and both have the difficulties at various levels, and they've made this subject challenging and interesting. But it's nice to remark that as of 2016, kind of string field theory reached a nice point where there's open string field theories, closed string field theories for pretty much everything, thanks to the work of many of these people in this conference, Ivo Satz, Yukawa, Kunitomo, Matsunaga, finishing earlier, finishing with the work of Sen. Now there's string field theories that kind of work for everything, and they will have to be understood better, and there's a lot of work ahead, and but anyway, it's a nice situation. So I will continue. So let's talk a little about string vertices, which is one of the ingredients of this string field theory. And you have the moduli space MGN of Riemann surfaces. And on top of that is bundle PGN, which corresponds for every surface sigma GN. The fiber is a set of local coordinates at the punctures. So if you have a surface here, this is a surface in the moduli space sigma 2, 2, genus 2 punctures. But by the time you have local coordinates around the punctures, you've constructed a point in this fiber. And we need to work with those local coordinates to compute off-shell amplitudes to define string theory. And as you know, there's also a projection that takes any surface and forgets about these disks that define the local coordinates and gives you back the moduli space. So the construction of string field theories has been emphasized many times. It's all about finding some kind of vertices, which are pieces of sections over the moduli space of Riemann surfaces. And there's been a lot of questions about whether this whole thing, this thing called FGN, should be a section. This is the part that comes from the string vertices. The rest comes from the Feynman diagrams, thus the F here. And should FGN be a section? And the answer is that it doesn't really need to be. It's nicer when it is, but it suffices that the map, the projection map from F to the moduli spaces of degree 1. And these things are clarified in our paper with Costello. As Ishibashi mentioned in his work, that perhaps at some point will be clear what is the relation with these things. The string vertices, you know, you have to put string vertices for 3 puncture spheres, higher puncture sphere, things like that. 1 puncture tora. You don't need a string vertex for genus 1 no punctures, nor you need a string vertex for a sphere with 2 punctures. Those are, in the first case, a constant term in the action. In the second case, is a kinetic term. The vertices are all such that the Euler number is -1, is smaller than -1, and they all admit hyperbolic metrics. This formal object called the string vertex should satisfy this recursion relation that's called the geometric master equation, in which the first term here is about gluing surfaces in this configuration, and the second term is gluing surfaces in that configuration. You remove disks, you remove the coordinate disk, glue, and twist in the case of closed string. This is the boundary of the region of the moduli space represented by the vertices. The lowest order expressions are that if you have a 4-point vertex, the boundary should match the sewing of 3 string vertices. If you have the vertex for a genus 1 surface with 1 puncture, it should match with the gluing of the 3 string vertex. And the action is constructed from these string vertices by this formula and satisfies the master equation. So these are things we did in this paper with Costello. I will not discuss it, but basically we emphasize that it's all about solving this equation, which was known. But once first that the solution should exist by mathematical arguments, that it's unique, and that the quantum master equation guarantees that everything works whether or not you have a section. Okay, how are you supposed to find string vertices? Well, one way is to put a metric on every surface and then use the metric to find disks and somehow to inspire you to define vertices. A term that I will use all the time is called the systole of a surface with a metric. Is the length of the shortest non-contractible closed curve, happens to be a geodesic. So given a surface with a metric, you just look for the shortest closed geodesic that you cannot contract, and that's the value of the systole, is the length. We always work with Riemann surfaces, so we really consider conformal metrics all the time. And one way to produce metrics is with a minimal area problem, in which for every surface you find a minimal area metric with some fixed systole. So you say all curves must have at least length 1, because that's what all closed curves must have at least length 1, all non-contractible closed curves. And there's geodesics that saturate the length condition, and they are of systole length, and the surface is covered by them. This is the story of minimal area metrics developed long ago, and for which, thanks to work with Matt Hedrick and Brandeis, we made some interesting progress. So for a 3-puncture sphere, you need all curves that were shown here must be of length at least 1. This is another way of thinking of the sphere, and sort of the metric looks something like that. Anyway, let's move to hyperbolic stuff, which is what we really want to discuss. So in nice work a few years ago, Musavian and Pius went back to the idea of using hyperbolic metrics. And indeed, as Ishibashi mentioned, it's kind of funny that throughout the history of string field theory, there's very little recorded attempts of using hyperbolic metrics, which are the most well-known metrics on Riemann surfaces. And you know, there is a basic difficulty with doing this exactly, as I will recount now, but actually there's a solution as well to that problem. So apparently we can do quite well with hyperbolic metrics, and that's a new development. So what did Musavian and Pius propose? Basically, they said, let's use the k equal -1 metrics on MGN. And this would be, for example, for a 3-punctured sphere. it would look something like that. A surface with 3 cusps. The cusp would be at infinite distance. It's a complete hyperbolic metric, and it's a nice metric. So you want to define local coordinates. So how do you do that? You can do the following. You can basically decide that the local coordinates are going to be bounded by the curve that has some particular arbitrary length. Curves that are homotopic to this puncture, for example, have bigger and bigger size as you move into the surface, and at some point they reach some number C star that you can pick, and you can decide that's where you're going to stop. Now, these curves are not geodesics. They're shown in this diagram. The surface is mapped to the upper half plane. The punctures are color-coded, so you can kind of see them. And these circles here are called horocycles. So Musavian and Pio said, well, let's choose some C star that is very small, because if it's not sufficiently small, it might happen that when you pick some length, they start crossing these things, complicating stuff. So you should pick it small. And the rule for vertices would be that any surface belongs to a string vertex if the systole of the surface is greater than C star. So the systole for this surface would be the length of closed curves, non-contractible closed curves, that there are none here. So this is satisfied in this case. All these curves here are contractible. But in general, you look at the non-contractible curves and you want these curves to be bigger than C star. So this was the rule for vertices. But there's a complication with that. Suppose you look at the boundary of the 4-string vertex. It would be at a place where one curve reaches the length C star. On the other hand, from the gluing, which is what is done in the right-hand side, what you're supposed to do is to take this 3-string vertex, this 3-string vertex, cut the disks and glue. That produces a curvature singularity. So these two surfaces are not the same, and that they were supposed to be the same. Another way of showing the obstruction is to say that, in fact, the Euler number of an hyperbolic surface tells you what is the value of the area. So any 3-string vertex, as you see here, has area 2 pi. So this one has area 2 pi, this one has area 2 pi, and any 4-punctured sphere must have area 4 pi. But by the time you cut these pieces and glue, the area is smaller than that. So there's something going wrong. So we're going to try to do this differently. Of course, the whole work of Musavian and Pius was essentially based on the idea that this thing could be repaired by a recursive procedure that they explained to first order based on nice work of Wolpert and others that can try to fix this, this problem by introducing new corrections. So hyperbolic tools, what we're going to do is pass from the punctured surfaces to the surfaces with boundaries. So at first sight, surfaces with boundaries are actually more popular in Teichmüller theory than the ones with punctures because they're a little easier to treat. So this is an attempt to do that. So suppose you have a genus G surface. The Teichmüller space, or just a surface, not even a Riemann surface, the Teichmüller space of this surface, or the Teichmüller space of genus G, is the Teichmüller space of hyperbolic metrics that you can put on this metric. As you change the hyperbolic metric, you change the conformal structure, you fill the moduli space. In fact, you're filling Teichmuller space. But suppose now you have boundaries, as we show here. You have the Teichmuller space of hyperbolic metrics with geodesic boundaries. That's the Teichmuller space as well, but it is too large. It's too big, this Teichmuller space. It essentially has like an extra coordinate per boundary. This is familiar in the case of pants. If you were doing pants, which is a surface with 3 holes, we know that this Teichmuller space with 3 boundaries includes all values of the lengths of these boundaries, the geodesic length of the boundaries. So it's too much because nu03 is a point, while you here have 3 coordinates, a 3-dimensional space. So what you do is you fix the length of all the boundaries. So if you have the Teichmuller space of genus G, n boundaries, all of them of length L, this is a Teichmuller space that has the same dimensionality as the moduli space. So if you pass to the moduli space from this Teichmuller space, you can do the following. You can, moreover, take any of these surfaces that have boundaries now. They all have n boundaries, all of length L. You can map to a punctured surface by attaching a semi-infinite flat cylinder of circumference L, where L is the size of the puncture. So this is done here. So this is a 3-string vertex, say, looking like 3 L's, and you attach 3 hyperbolic, to the hyperbolic metric, 3 infinite tubes. So there's a natural way to go from surfaces with geodesic boundaries to surfaces with punctures. And it was defined in the mathematical literature by Mondello and others as GR infinity, which is the map that adds those infinite cylinders. The great theorem, some people say it's kind of obvious, but these people work hard to do it, is that this moduli space here of genus G, n boundaries L with the cylinders attached is topologically equivalent to the moduli space of Riemann surfaces. So it produces essentially a whole section here. So basically, that's what we really wanted. So how are we going to identify the vertex region? It's going to come, okay, it's going to come soon. You know, I started 10:22, so I think I need a little more time. Please recalculate. So here's a little result that makes all the difference. Color theorems. If you have a geodesic, you can define a color, which is a little annulus that surrounds the geodesics. So there is a length W that you can use here that is calculated from this formula. If your geodesic has length L gamma, put into this formula cinches and calculate WL, which is the total length of the annulus. And the nice theorem is that if you draw that color, the colors are disjoint on the surface. So whenever you draw all these colors on separate curves, the colors never touch. So the colors are disjoint, and there's a particular value that is quite useful, is the value L star, for which this number is 1, is 2 arc sinh 1, and therefore omega L is the same as L star. So if you choose any length L for your boundaries of your diagrams that is smaller than L star, your W is going to be bigger than L, and it's going to be quite big, the color. So the boundary of a color is half length. So here are the hyperbolic string vertices. You simply take the string vertex to be all these surfaces in this moduli space of genus G and boundaries length L, such that the systole is bigger than L. And then you attach cylinders. So the claim is that this new G and L with L less than L star solves the master equation exactly. So you look at the moduli space as you travel here. Sometimes there's going to be short curves, so you don't pick those. But if all the curves, non-trivial closed curves here, are bigger than your number L, that is smaller than that L star, then you pick it. So it's a clear definition, and given the pressure of time, I will not explain exactly why this works, but the basic argument is that when you saw together any two surfaces, the colors are such that you don't generate short curves. You basically have two surfaces in which there's no short curves, they're in their vertices. But then when you glue them together, you don't want short curves, but any short curve has to cross the new geodesic where you glue together, but they're the colors and they cannot be too short. So getting to the end of this, there's a Feynman region in addition to the vertex region. And the Feynman rules, Ishibashi again also mentioned that there's difficulties on using hyperbolic metrics for the propagators. In fact, they don't work because the boundaries are not geodesics and they make life very difficult. So the idea for us is we might have hyperbolic metrics, but when a propagator is born, we put the flat metric in here. So the metric is a little bit of a hybrid, hyperbolic on the string vertices and flat on the annulus. As it turns out, this metric that at first sight seems a little weird is not that strange. It's called Thurston metrics. They've been explored in the literature, and this is a metric on a Riemann surface. It's a Thurston metric if it's composed of annuli with flat metrics and circumference less than L, and hyperbolic junctions with metric and systole greater than L. Hedrick has conjecture, and we're trying to prove that in fact these diagrams are also solutions of a minimal area problem, one in which you want the systole is greater than L, but in addition you want the curvature to exceed -1. And under those conditions, it seems to us very likely that the Thurston metrics arise. There's a lot of intuition for it. And Thurston himself and his followers demonstrated that in the theory of measured laminations, this metric that is mixed is it's really the natural metric. So, so we think it's probably all good. So let me just finish. I think with this construction, there's probably the first explicit construction and completely rigorous. The minimal area metrics have not quite been shown to exist at higher genus. We believe they do exist, but if you're talking rigor, you don't quite have a perfect mathematical theorem there. Here, these metrics exist, these subsets exist, they're compact, it's all fine, and it's all very explicit, and it's all very exact. The action is purely hyperbolic because the action is constructed with the vertices. Let me mention that there's a limit of the classical theory in which if you take this L going to infinity, you get the minimal area classical string field theory. So I mentioned this work going on with Hedrick. The computation of the action, I would say that maybe let me do a little diagram here. Suppose we want to get here. Minimal area metrics have sort of started well, but has gotten difficult. Hyperbolic metrics, I believe, are very promising. They will maybe reach all the way here because of work of many people doing integrals with that. But we don't have this part yet, the ramp. We don't even know how to compute the general version of this thing off shell at this moment. And a grad student at MIT is looking at it. Many other people may be looking at it. I think there's a lot to do. All right, that's all. Thank you.
Okay, so thank you for your talk, Barton. So we have time for some questions. So I'm not sure whether maybe I'll call on Ezra.
Yeah. Yes. Hi, Barton.
Hello.
So you mentioned you wrote homeomorphism when you quoted Mondello's result.
Yes.
Is it better? I mean, how much like?
It's a mapping class group invariant homeomorphism.
So can you say, is it a little better that homeomorphisms could be quite wild? Is it a little better? I mean, are there any regularity properties at all?
Well, you know,
Lipschitz, Hilda, anything. I mean, I assume you're excluding that it's differentiable by saying homeomorphism. That's really my question.
I'm not sure. I think it probably is differentiable, but I couldn't tell for sure. I think it's a pretty nice homeomorphism, actually.
But what do you use the construction in your work, or is it was this purely just to illustrate the background to your construction? I didn't quite follow.
Well, it was useful in order to, let me see if I can find this. It was useful in order to, here, in order to claim that it produces a section over the moduli space of Riemann surfaces. That's it. Now, as it turns out, once you produce a section, we know that the vertex region, the piece that we chose for the vertex, is a section, which is something quite nice.
Yes,
the part that we still don't know is the Feynman region, modulo some results, more results on the third side. You see, on the Feynman region, you really depart from the Mondello section because you're introducing this flat annuli as opposed to hyperbolic metrics. So we have a section over the string vertices, but not quite a proof that the Feynman region is a section.
Right. Okay, thanks.
Sure.
Okay, so there are a lot of questions. I have too, but I think because we're supposed to start exactly at 5 and we already have less than 10 minutes break, maybe we can stop now and we can try to ask Martin later. And
okay.
Yeah, so let's take a break and we'll be back in 9 minutes.
Mohab, if you have a question, you can just go ahead.
I have a question. So this L can be served as a cutoff, right?
This L, yeah.
Yes. So when L goes to 0, so you have a kind of a homotopic for the vertices.
Well, L goes to 0 is a limit. You don't want to take L equal 0 ever, but if L goes to 0, is yes, it's allowed. It's very long propagators, and I don't think it's it would reduce and become more into the construction. Presumably, in the L going to 0 limit, it turns into, well, not quite. I was going to say Musavian and Pius, but it's not exactly that either, because they sort of magnify the region of the punctures a little bit. So I think it's still different.
Okay, so that corresponds to the boundary of the modular space.
Yeah, well, L going to 0 would correspond to very fat vertices in which pretty much everything is on the vertices.
Right. So for this cylinder, you have a flat matrix. So that's consistent to have a Lorentz signature of propagator.
Yes.
Yeah.
Right. It's allowed. Right.
Yeah. So what is you have Riemannian, but the propagator you have Lorentz signature.
I'm not sure what is the question.
So the vortex, we have this Riemannian matrix.
Right.
But for the propagator, you have Lorentz signature.
Well, no, I don't have, as usual in the string diagrams, you take everything to be Euclidean. So it's true that on the cylinders, you could put a Lorentzian structure, but you don't have to. So we really think of the surface as just a standard Riemann surface with Euclidean coordinates anywhere.
Okay, I have a comment. It's not really a question, but first of all, it was a beautiful talk.
Thank you, Jim.
Brought me back to pictures I saw many years ago, now updated. But in particular, your first set where you had the singularities in the 3/8, yeah, that's fine there. Okay, if you think of those before you cut anything out, I put on the chat a paper of Igor Riven's, which has some very interesting comments about having not just 3 coming together, but any number, a polyhedral description, which kind of brings back memories of when you guys were looking at polyhedral decompositions.
I see.
So it's a reference there for anyone who's interested. That's all.
Thank you. Thank you. Very good. All right. So I'll give up this. Stop broadcast.
Hello, are people here? Okay. Next talk is from Mritunjay Verma, and he's going to talk about open-closed superstring field theory. Are you there?
Yes, so thanks. So let me share the screen. So is my screen visible?
It's visible to me.
Okay. So let me begin by thanking the organizers for giving me this opportunity to talk. So this is a work done with Farooq Musavian and Ashok Sen. So the brief outline of my talk is, first I will talk about some general introduction, and then I will talk about construction of open closed string field theory, and then this will be about the oriented open closed string field theories, and then I will talk about generalization to unoriented strings. So so as we all know, string field theory is the field theoretic formulation of string theory. And the usual string theory based on Polyakov prescription relies very heavily on worldsheet conformal field theory. The worldsheet CFT does give a powerful tools which allows us to explore the theory deeply. However, it also puts some restriction on how far one can go. The worldsheet calculation typically give some IR divergences, and one can trace these divergences to be coming from boundary regions of the moduli space. And some of these divergences can be cured within the framework of worldsheet theory by making an analytic continuation in the external momenta. However, for some of the problems, such as mass renormalization of generic string state, tadpole divergences due to working with incorrect vacuum state, or the contribution of Dean Stanton to perturbation theory, about which we had lectures from Ashok last week, the analytic continuation is not enough. And during the last few years, string field theory has given systematic tools to deal with these IR issues. String field theory has also given a deeper understanding of the issues of unitarity and analyticity in string theory. And it has also been used to study the superstring in RR background. And apart from perturbative questions, it has also given insights into non-perturbative aspects of string theory. So for example, many talk we heard the following Ashok's work on tachyon condensation, a lot of results have been obtained both analytically and numerically regarding the open strings in D-brain backgrounds. So with this motivation, let me begin the context of this talk. So the bosonic closed string field theory was developed in early 90s and provides the language we shall be using. The closed superstring field theories has been constructed recently. The open superstring field theory was first string field theory was first constructed by Edward Witten. However, it was soon found that it contained divergences which correspond to propagation of closed string states. And there has been various attempts to reformulate the open string field theory so that these divergences appear. However, at the full quantum level, this is still incomplete. And one way to deal with these divergences is to explicitly add the closed string sector to the open string field theory, which leads to combined open closed string field theory. And such systems naturally arise in the presence of D-branes. For the bosonic case, the combined open closed string field theory was constructed by Barton. And our goal will be to describe the supersymmetric version of the combined open closed theory. So before proceeding further, let me describe the schematic way in which all these string field theories are typically constructed and viewed at present. So string field theory, string field is a generic linear combination of all the string states which appear in the first quantized worldsheet theory. So in this expansion, psi equal to sum over r psi r phi r, where phi r denotes the basis states. So these basis states are in one-to-one correspondence with the states in the worldsheet theory, and psi r turn out to describe the space-time fields. The usual string theory, which is based on Polyakov prescription, it gives a formal expression for the on-shell amplitude, which is given as integral over the moduli space. So in this integral, this V1 to Vn is a correlation function of vertex operator and ghost and picture changing operator on a generic on a genus G Riemann surface, and mi denote the coordinates on the moduli space. And so to go to the string field theories, one generalizes this to construct the off-shell amplitudes, and this involves making the amplitudes depend upon some off-shell data such as local coordinates around the puncture and PCO locations. One now divides the integration region in 1PI and 1PR parts. So the 1PR part include those regions in moduli space which correspond to separating type degeneration of Riemann surfaces. On the other hand, the 1PR part includes those regions which correspond to separating type degeneration, but 1PI part excludes the separating type, though they include the non-separating type degeneration. And identifying the 1PI and 1PR parts of amplitudes, one can construct the vertices of a string field theory to be used in the action. So for example, if one is interested in 1PI effective action, then one will have to integrate these correlation functions over the region of moduli space which are free from separating type degeneration, but which include the non-separating type degeneration. And if one is interested in the elementary vertices of the theory, then one needs to exclude all type of degenerations. So this is just a schematic representation of, so in separating type degeneration, basically a Riemann surface degenerates into two, and in non-separating type degeneration, it develops a handle. So with this introduction, let me begin the construction of open closed string field theory. So we start by introducing the vertices which shall be used in the construction of the 1PI action. So for this, we introduce some specific vector spaces in which string fields live. So in this, in these expressions, HMN denotes the vector space of closed string states with picture number m, n, and HM denotes the vector space of open string states with picture number m. So for example, vector space HC denotes the sum of states in NSNS, RNS, NSR, and RR sector. In the formulation, we shall be using the states with picture number -3 of also play a role, and which has been denoted by this H tilde. So for fields psi IC belonging to HC and psi IO belonging to HO, we denote the off-shell 1PI amplitude with this expression. So in this expression, RGMN is the part of moduli space of punctured Riemann surfaces, which includes information about the local coordinates around the punctures and PCO location. So this RGMN is essentially the vertices which Barton was talking about in the previous talk. And omega p is the correlation function on the Riemann surface, and p denotes its dimension. So one needs to integrate this over this part of the moduli space, and we have a factor of this gs to the power 2g minus 2 plus v, which is essentially the weighing the genus G contribution with string power, I mean with Euler number. So in this definition, the disk 1 point function is not included. We need to treat this separately, and the reason for this is that in the RR sector with picture number -12, the quantity psi c semicolon vanishes, since it cannot satisfy the picture number conservation. So on Riemann surfaces with boundary, the total picture number is the sum of left and right moving sector. So for these states, the total picture number will be -1, and even if we include the picture changing operator, we cannot satisfy it because picture changing operator have picture plus in positive picture numbers. So but for elements in S tilde C, there is no problem. In the RR sector, they carry the picture number -3/2. So a total picture number -3. And by inserting one picture raising operator, we can satisfy the picture number conservation on the disk. Hence, for psi tilde c belonging to h tilde c, we define this one point disk function psi tilde c d to be the contribution from one point function on the disk. For the NS sector, we can include the disk one point function contribution either in this psi c semicolon or this psi tilde cd. For uniformity, we include it in the definition of psi tilde cd. The basic reason that the disk one point function needs these states from h tilde c is that the d branes carry the RR charge and they couple to RR potential. This is contained in psi tilde c. The psi c, the states with picture number -, they contain the RR field strength. So that is why we need the states from psi tilde c to couple to d branes or disk one point function. So before proceeding further, we note some features of this section segment RGBNM. This section segment, as I mentioned earlier, must not contain any separating type degeneration. And given two section segment, we can generate new section segments by repeated applications of plumbing fixture and hole creation operations. In the plumbing fixture, we take two section segments RG1 B1 N1 M1 and RG2 B2 N2 M2. We now pick a Riemann surface from one family and see one of its puncture to a puncture on the Riemann surface from the other family by identifying the local coordinates around the puncture. So for closed string, the gluing relation is W1 W2 is equal to e to the power -s minus I theta, and for open string it is W1 W2 equal to -e to the power -s. On the other hand, in the hole creation operation, the Riemann surfaces from the section segment RGBNM are glued to a disk with one closed string puncture, with the gluing relation W1 W2 equal to e to the power -s. And this needs to be specified separately since the disk with one bulk puncture is special in the combined open closed superstring field theory. Note that there is no factor of this I theta in the gluing relation, and this is due to the fact that on the disk with one puncture we have a conformal killing vector. Now a very useful identity satisfied by these curly brackets and one point function on disk is the so-called main identity. So for the states in psi tilde c, it takes a very simple form, the first line of this slide, and for the states in HC and HO, it takes this complicated form. So basically this identity includes the information about the degeneration of Riemann surfaces. So essentially, when you act QB with this correlation from this curly bracket, then one can relate the, one can use the Stokes theorem to write the integral as the integral over the boundaries of these regions RGBNM, and the boundary of RGBNM are essentially they essentially correspond to these S equal to 0 parameter of these plumbing fixture relation, and so these three terms in the right hand side of this identity, so they basically come from open string gluing and closed string gluing and this hole creation process. So in this expression we have these some special things, so like this BC and BO, so they are defined by this expression. So BC and BO are essentially the multilinear string states, and they are defined via these inner products, via these BPG inner products. And this operator G, which appears in these expressions, so that is essentially given by identity in the NS sector and given by the zero mode of picture changing operator appropriately in the R sector. So having described the 1pi vertices, we can now write down the 1pi action for the open closed SFT. So in the right hand side, first two terms describe the kinetic term for the closed string sector, and middle two terms describe the kinetic term for the open sector. The first term in the last line corresponds to gluing with the coupling with the D brane, and the last term is the interaction term. This special state, this square bracket with D, that is essentially related to the boundary state of the D brane system. Even though this tilde psi tilde C and psi tilde O fields appear in the action, they decouple from the physical processes, as we shall now argue. So the equation of motion one can derive from this 1pi effective action are these. So for the four fields, we have these four equations, and by combining appropriately these equations, one can obtain the equation of motion for the physical field psi C and psi U. These psi tilde C and psi tilde O can be determined after fixing a solution for psi C and psi U from this, and they are defined up to the freedom to add solutions to QB psi tilde C equal to 0 equal to QB psi tilde O. So this implies that psi tilde C and psi tilde O represent the free field degrees of freedom, and they completely decouple from the interacting part of the theory. And one can do a more careful analysis of this and finds that once you have found the solution for psi C and psi U, there is no obstruction to finding the solution to psi tilde C and psi tilde O. So this theory has a natural BB structure, and it can be shown that the 1pi effective action satisfies the classical BB master equation. Using 1pi action, we are supposed to work at the tree level. So this is the reason that this 1pi effective action satisfies the classical BB master equation, which corresponds to tree level theory. So for this, we identify the fields and anti-fields of the theory. And this is done by dividing the Hilbert space of the theory in this way. So for example, HC has been, so basis states in HC, they are separated into host number with greater than equal to 3 and host number less than equal to 2. So phi r plus, this var phi r plus corresponds to basis states with host number greater than equal to 3, and this phi s minus corresponds to host number less than equal to 2. For open string sector, the plus basis states correspond to host number greater than equal to 2, and minus basis states correspond to host number less than equal to 1. And so the non-zero inner product is given by between these pairs of the basis states. And using this division, one can expand the string field in the following manner. And with this, one can consistently assign positive, which is greater than equal to 0 Gauss number with the coefficient fields, the psi CR, psi tilde CR, psi UR, and psi tilde OR. So basically, the relation between the Gauss number of basis states and the Gauss number of this coefficient field is that the Gauss number of coefficient field is given by 2 minus coefficient 2 minus Gauss number of basis state for the closed sector, and for open sector it is given by 1 minus Gauss number of the basis state. And so consequently, for the BB quantization, the unstarred fields are interpreted as fields, whereas starred fields are interpreted as anti-fields. And now, using the main identity, this field expansion and the properties of the basis states, one finds that the 1pi effective action satisfies the classical BB master equation. The main identity also implies that the 1pi effective action is invariant under this set of gauge transformation. And these lambda i's are various gauge transformation parameters. So in defining the interaction vertices, we need to make a choice of PCO location and or the local coordinate system around the punctures. And these different choices of section apparently define different string field theories. However, it can be shown that all the string field theories defined this way are related by an appropriate field redefinition. More specifically, consider two SFTs which are defined using nearby section. Let this epsilon O and epsilon C denote the open and closed string field equations of motion. Let the variation in these equations due to the change in section be delta hat epsilon O and delta hat epsilon C respectively. Now under a string field redefinition, under which open string field changes gets defined by this delta tilde psi O and closed string field gets defined by delta tilde psi C. We denote the change in epsilon O and epsilon C by delta tilde epsilon O and delta tilde epsilon C. The independence from the choice of integration subspace means that these two variations cancel each other, possibly upon using the equations of motion. And one can show that using a string field redefinition of this form, this section independence essentially follows. So in this phi and psi are arbitrary open and closed string states. So with this, let me move on to generalization to unoriented theories.
You have 5 minutes.
Okay. So there are essentially two types of open-closed superstring theory, type 1 and type 2 with D branes. The open-closed superstring field theory we have constructed describes the type 2 superstring theory with D branes. And we so far we considered only the oriented strings. Type 1 theory is obtained by orientifold of type 2b theory. And we now describe the essential differences which one encounters while considering this case. Type 1 theory includes the oriented as well as unoriented strings. The unoriented strings are obtained by making an orientifold operation. This corresponds to taking a projection by the world sheet parity operator, which is possibly accompanied by some symmetry transformation acting on the world sheet superconformal field theory. So this means that in the vector space in which string fields live, we need to introduce orientifold projection. All the sieving now should be done with this projection. This automatically gives rise to unoriented surfaces like Mobius strip and Klein-Botter. Denoting the world, suppose we denote the world sheet orientation reversing operator by W. The sieving should include this projection operator, E equal to 1 plus W by 2. Due to the inclusion of this operator in the sieving operation, one needs to include some numerical factors in the definition of these curly brackets to ensure correct factorization near degeneration. These curly brackets do not refer to any specific CFT. Hence, apart from the above changes, essentially the same construction as in the oriented case can also be applied to the unoriented theories. The main new feature in the case of unoriented string field theories are, I can summarize as follows. So that this definition of these Hilbert spaces HC, H tilde C, HO and H tilde O include the appropriate orientifold projection operator. The official amplitudes now includes the sum over moduli spaces of oriented as well as non-orientable surfaces. The psi tilde C D, which was earlier only denoting only the disk 1 point function, now also includes the 1 point function on RP2, that is which is sphere with one cross cap. And this definition of this curly bracket gets modified in this way. So we now have also sum over the cross sum over the cross caps, and we will finish.
Okay, I think I didn't hear you for the last moment. I'm not sure whether it was my computer or your computer.
I don't know.
Did other people hear him?
From which slide?
We couldn't hear for a second.
Yeah, I lost the last minute also.
Yes.
Okay. No, I was just saying that with this modification, one can use this string field theories for the unoriented theories also.
Okay. Okay, so so are there any questions for Mritunjay? Okay, we have a question from Yifan Wang.
Hi, I have a question. Is there some understanding of type 1 heterotic duality at the level of the string field theory?
Okay, I'm not aware of this, but probably one can try to study this question.
I mean, since you talked about the identifolds in type 2p.
Yeah. Okay, so I mean, I have not thought about this question, but probably, I mean, one can try to find out. I mean, one can use this construction to see if there is, I mean, what string field theory has to say about this.
Okay, are there any other questions? So I had a question. So when you were talking about the 1pi effective action for the open closed string. So this is okay. This is described by a described by an L-infinity algebra, right?
Yes. Yes.
Or okay, so this, I guess, okay, so there's also this notion of the open-closed homotopy algebra, a classical open-closed homotopy algebra, which I think is discussed by Kajiura and maybe Stashev.
Right. Yes.
So I was never quite sure what this means physically, because it's not clear.
I mean, what does not mean physically?
So if you're considering quantum open strings, if you have closed strings, then you're considering quantum open strings. And once you're considering a quantum effects, then in principle you should include all diagrams or contributions from every genus.
Right.
So I guess this is a setup where you could interpret such a structure, this classical open-closed homotopy algebra. I also don't know if you have any physical comments as to whether there's some okay, outside of the context of the 1pi framework, if there is some understanding of a classical open-closed string field theory physically.
I'm not sure if I understand this correctly, but yeah, I mean, here we have, I mean, here the theory only has this L infinity structure in this formulation. And when you consider this I mean, the full, not the 1pi, but also the full quantum BV master action. So that also can be formulated in terms of purely L infinity algebra. So maybe, sorry?
Did you say a quantum L infinity or?
I mean classical. Okay. I have not thought about this, but.
Okay.
But maybe there is some relation between this open closed this algebra and. Okay. I'm not sure.
Okay, I was just trying to get some insight into this question, which I never really. Okay. But
I mean, in this formulation, we have given up the A infinity structure. Yeah. We can probably recover it with some effort, but we don't see it directly. I mean, we only see the L infinity structure.
So you consider the 1pi effective action, right?
Or even the quantum effective action, which will have the quantum L infinity. But the A infinity is not visible in this formalism.
Yeah, so this is actually not what I'm asking about. I was more trying to understand whether there was a physical setup where one can give a meaning to a classical open-closed string homotopy algebra. So it seems that, okay, if you keep track of the color factors appropriately, then that physical setup could be given by the 1pi effective action of open-closed string field theory. Okay, and that didn't occur to me before, but maybe there's also some other natural way of thinking about classical open-closed string field theory outside of that context, but I'm not sure I understand it. So I was just asking whether there's some, yeah, okay. So I think I think now we should move on to our next talk by Ruggero. Are you online somewhere?
I'm here. Do you see me?
Yes.
Okay.
Okay. So so now we will hear about the simple solution for static backgrounds in cubic superstring field theory. Okay. So so continue.
So first of all, I would like to thank you, the organizers, for giving me the opportunity to present this talk today. And this talk is based on a paper published last year with Theodor Erler and Carlo Maccaferri. And today I will also present some results that we are currently working on. So the main topics that I will discuss today are the following. I will start by describing the general properties and features of the solution, which was already discussed by Carlo Maccaferri in the previous talk. And then I will focus on the superstring case, and we will see under which conditions the solution is well defined as a string field. We will then see that by enlarging the set of fields that are allowed in our algebra, these conditions will become milder. We will then proceed with the analysis of the obtained solution, and we will end up by considering a special case which was prohibited before introducing the new fields, which is the simple solution case. So let us start by remembering that in 2014 and 2019, Erlen and Maccaferri studied a set of solutions of the equations of motion of cubic open string field theory, showing that it was possible to describe a generic set of d-branes starting from a known one. So they considered the strings that were stretched between the two sets of d-branes that shared the same closed string background. Such a solution was called the intertwining solution, and it relies on a tachyon vacuum solution, and in particular on the so-called intertwining fields, which are denoted here with sigma and sigma bar. They satisfy the following three properties. So they are the intertwining string fields are annihilated by the shifted BRST operator around the tachyon vacuum, and we moreover have that sigma bar sigma is equal to 1. The explicit expression of the intertwining solution is given by this formula, where the first tachyon vacuum here is the tachyon vacuum in the reference boundary conformal field theory, whereas the tachyon vacuum here sandwiched between sigma and sigma bar is the tachyon vacuum in the target boundary conformal field theory. The intertwining string fields are in general built in terms of flux states, and their construction can be complicated in general. One way to avoid this problem is to consider the particular case of static backgrounds in which the time component of the BCFT remains unaltered. In this case, the intertwining string fields sigma and sigma bar are written in the following way in terms of BRST variation of some object, which is written again in terms of small sigmas, which are insertions of weight 0 superconformal primaries. These small sigmas can be written as a product of an exponential of the time component of the time direction and boundary condition changing operators of generic weight h. So the first term, the exponential term, is needed in order to obtain a weight 0 operator. And with these operators, we have the following OPE. So the OPE of sigma bar and sigma is equal to 1, whereas the OPE of sigma and sigma bar is G star over G0, where G star and G0 are the disk partition functions in the respective BCFTs. These string fields can be built in terms of flux states, and they correspond to the limit L that tends to 0 in the height of the horizontal strip of the flag. And this is only possible when operator insertions are of conformal weight 0. So we have seen that by going through the Tachyon vacuum, we annihilate the starting de-brane system, and from the Tachyon vacuum, a new de-brane system emerges. For example, one can describe the translation of a de-brane in a certain direction, which can be taken, for example, to be x1, over a distance d. In this case, the boundary condition changing operators are written in the following way, where the first term in the exponent is the one needed in order to obtain a weight 0 operator, whereas the second one is needed in order to translate the de-brane. Here x tilde 1 is defined in the following way. Another example, maybe more interesting, could be the creation of de-branes of codimension 2n. So we can consider strings which are stretched between a dp brane and a dp plus or minus 2n brane. In these cases, the boundary condition changing operators are written again as a product of an exponential factor which is needed to obtain a weight 0 operator. Then we have delta and delta bar, which are twist fields which account for the change in the boundary condition of the bosonic direction axis. And we finally have the spin fields, which are given here in their bosonized form in terms of the chiral bosons Hi, which are needed in order to change the boundary conditions of the fermions. So the explicit form of the solution relies, as said, on the Tachyon vacuum, which is given here in the Yukawa form in terms of the generic function f of k, which satisfies the following requirements. And the intertwining solution is given by this formula, where, for example, we can notice this the first term is the Tachyon vacuum. In this formula we left the BRST variation of sigma generic. We didn't substitute the explicit form. And by conj we mean reality conjugation of the term on the left. So we have to read this term, for example, from right to left. So square root of h, sigma, square root of f over h, and so on. Here the h of k is 1 minus f of k divided by k, and it is the usual homotopy string field, and it is the operator that trivializes the cohomology of the shifted BRST operator, as indeed the QTV applied to the product B times H is equal to 1. By substituting the BRST variation of weight 0 matter operator, which is given in this expression, where it is C del sigma plus gamma supersymmetric variation of sigma, one gets the explicit form of the solution. The intertwining solution by construction satisfies the equations of motion, but one has to be careful, and one has to check that the solution as a string field is well defined. So one has to check that it does not contain OPE divergences, and that the term psi squared appearing in the equations of motion does not contain the triple product sigma, sigma bar, sigma, or also sigma bar, sigma, sigma bar. Indeed, these triple products lead to associativity anomalies of Witten star product, as can be seen from the following short computation. from the right, we see that taking the parentheses in a different way leads to different results. So on the right, we have sigma, whereas on the left, sigma sigma bar is G star over G0, so we have G star over G0 times sigma. In general, G star and G0 are different, so this is a true associativity anomaly. So in order to address this potential problem, we make the following assumptions. So the OPE of sigma and sigma bar is regular, and this is satisfied by construction of the boundary condition changing operators. Whereas we also we also require that sigma and the OPE of sigma and the supersymmetric variation of sigma bar is irregular again. This condition has been checked in all the examples that I previously mentioned. As a consequence of these assumptions, we have, for example, that the OPE of sigma and the derivative of sigma bar is less singular than a simple pole, and so on. So, as a consequence of these assumptions and these other results, one can impose some conditions on the function f of k, which appears in the Tachyon vacuum. To see this, in order to be concrete, one can take, for example, a one-parameter family of functions f of k, like this, parameterized in terms of a real number nu that has to be less than 0. Nu is the leading level in the expansion k that goes to infinity, and this expansion can be formally encoded in the so-called dual L- expansion. In particular, the limit nu equals -1 is the simple solution, whereas nu that tends to minus infinity is a Schnabel solution. The operator L- allows to control the behavior of the solution towards the identity string field, which is the one responsible for worldsheet collisions. So using this formalism and using this expansion, one can prove that the leading level of the function f of k, in order to have a solution which is free from OPE divergences and associativity anomalies, for the bosonic solution has to be less than 0. So in the bosonic case, where all the terms containing gamma are 0, in that case, the simple solution is allowed. The simple solution is the one at nu equals -1. In the supersymmetric case, instead, nu has to be less than -1. So for the superstring, this upper bound excludes the simple solution. In order to understand better, let us see what happens exactly at nu equals -1 in the simple solution case. The following two terms show up in the solution, and they are perfectly fine from the OPE point of view, but they lead to the ill-defined products sigma bar, sigma, sigma bar in the computation of psi squared. Indeed, for example, when we multiply this term by this bosonic term appearing in the solution, we obtain an associativity anomaly. So up until now, we have seen that the intertwining solution is not divergent and it is not ambiguous, provided that nu is less than -1 in the superstring case, and in the simple solution case, we have seen how the associativity anomaly arises. Let us see how to solve this problem and how to improve the behavior of the solution. One way to solve this problem is to embrace worldsheet supersymmetry and to consider supersymmetric variation of string fields as their commutator with the string field G. G has been already introduced and defined by Erler in 2011, and it consists on the insertion of this infinite vertical line inside an infinitesimal width strip. This is perfectly analogous to what is done for worldsheet derivatives, as the derivatives of operators are written as commutators with the string field K, and the string field K is defined in the same way as G, but here instead of TF, we have the usual energy momentum tensor. Notice that the product gamma G, which will appear in the solution, does not change the GSO sector of the boundary condition changing operators. As for example, if sigma is in the GSO plus sector, then the product gamma times the commutator of G sigma will be again in the same GSO sector. This new string field G satisfies the following relations. So G squared equals K is the usual, is a known fact that the supersymmetry transformation are the square root of translations. And we also have that G commutes both with B and K. And we also have that the BRC variation of G is 0. Here, for these brackets, we use this definition in terms of the Grassmannality of the string fields. This bracket generalizes, extends the one used for the bosonic algebra, for the usual KBC algebra, for example. Alternatively, one can tensor the whole algebra with internal Champato factors, and in that case, one would have to use the effective Grassmannality, which is written as the sum of Grassmannality and the fermion number. This is not strictly needed for our analysis, so we will proceed with our choice. So before checking the result for the generic f of k case, let us focus on what happens at nu equals -1 in the simple solution case, where f of k is 1 over 1 plus k. The previously mentioned and analyzed terms are written in the first line. This second term can be rewritten in terms of commutators, like this. From these two commutators, 4 terms will arise. One of them is GBG, which can be rewritten as BG squared. But now we know that G squared is K. And by summing and subtracting 1, we see that this term cancels out with this one. And one is left with this term, which is perfectly fine from the OBE point of view, and which is not anomalous. So it would seem that introducing the string field G allows to improve the behavior of the simple solution. So in order to be precise, let us focus. Let us then move on to the generic f of k case. So in this case, the solution is given by the following formula, where I want to stress out that I want to remark the importance of these red terms. Indeed, they are the ones that cancel out in the simple solution case, as in the simple solution f is equal to h. So this term perfectly cancels out with the other one. And we also have that this third term is the one is the one that remained in the previous slide. So one can repeat the analysis done in the main paper before introducing the string field G for this new solution. If one does that, one can prove, for example, that the solution is well defined, provided that the leading level in the dual L- expansion of the function f of k is less than -1/2. So this is a milder bound compared to -1, and this allows to study the simple solution case at nu equals -1. In this case, the intertwining solution can be written in the following way, where the first term is again the usual Tachyon vacuum, where the second term is the term which we analyzed before, the one remaining. These 3 more terms are written in terms of chi and chi bar, which are string fields which I defined in the following way. they enjoy a nice set of properties. And so, for example, one sees that the BRC variation of sigma and sigma bar can be written in terms of commutators with of chi and chi bar, respectively, with sigma and sigma bar. Chi also satisfies the following two properties. So the commutator of chi and b and chi bar with b is 1 plus k, and chi bar minus chi is 1/2 the derivative of c. These properties are the key in order to double check, for example, that this simple solution does indeed satisfy the equations of motion. Indeed, we remember that we have to prove that the intertwining string fields satisfy the following property, that sigma bar sigma is equal to 1. And by using these relations, one can prove this formula. And in order to prove the remaining ones, which are the fact that the intertwining string fields are annihilated by the shifted BRC operator, one has just to use the usual supersymmetric variations of the ghosts C and gamma. So as final remarks, I can say that just as realizing that the derivative of the boundary condition changing operators could be written as commutators with 1 plus k allows to improve the behavior of the bosonic solution from a leading level nu less than -2 to nu less than 0. Here in the superstring case, realizing that the supersymmetric variation of boundary condition changing operators can be written and expressed in terms of this string field G, allows to lift the bound from nu less than -1 to nu less than -1/2. This in turn allowed to study a simple solution which is now free from OP divergences and associativity anomalies. Finally, it would be interesting to investigate more cases of de Bruijn transitions and to further understand and study the flux solution for the superstring case. Another fascinating idea would be to upgrade the obtained solution to the Vestuminovich and Berkovits open string field theory, as it is known that solutions of the cubic in the cubic approach are the first step in order to obtain solutions of the non-polynomial equations of motion. That's it. Thank you very much for your attention.
Okay, thank you. So do we have any questions? It seems we do not. So so maybe I will thank the speaker and say it was a great day at this conference, and I guess everybody can now go to sleep or okay. So I think that's all for now.